space with some velocity, it has some speed going in some direction, and maybe it's deep space, and we can just for purity assume that there's no gravitational interactions. There'll always be some minuscule ones, but we'll assume no gravitational interactions, absolutely no particles that it's bumping into, absolute vacuum of space. This thing will travel on forever. Its velocity will not change. Neither its speed nor its direction will change. So this one is absolutely true. Statement number two. An unbalanced force on a body will always impact the object's speed. And the key word right over here is speed. If I had written impact the object's velocity, then this would be a true statement. An unbalanced force on a body will always impact the object's velocity. That would be true, but we wrote speed here. Speed is the magnitude of velocity. It does not take into account the direction. And to see why the second statement is false, you can think about a couple of things. And we'll do more videos on the intuition of centrifugal acceleration and centrifugal forces, inward forces. And this does not make complete intuitive sense to you just at this moment. But imagine we're looking at an ice skating rink from above, and you have an ice skater. This is the ice skater's head, and they're traveling in that direction. Now imagine right at that moment, they grab a rope that is nailed to a stake in the ice skating rink right over there. We're doing all of this from above, and this right over here is the rope. Now what is going to happen? Well, the skater is going to travel. Their direction is actually going to change. And they can hold on to the rope, and as long as they hold on to the rope, they'll keep going in circles. And when they let go of the rope, they'll start going in whatever direction they were traveling in. When they let go, they'll keep going in that direction. If we assume it's very, very, very small frictions from the ice skating rink, they'll actually have the same speed. So the force, the inward force, the tension from the rope pulling on the skater in this situation would have only changed the skater's direction. So an unbalanced force doesn't necessarily have to impact the object's speed. It often does, but in that situation, it would have only impacted the skater's direction. Another situation like this, and once again, this involves centrifugal acceleration, inward forces, inward acceleration, is a satellite in orbit, or any type of thing in orbit. So if that is some type of planet, and this is one of the planet's moons right over here, the reason why it stays in orbit is because the pull of gravity keeps making the object change its direction, but not its speed. Its speed is the exact right speed, so as it travels, so this was its speed right here. If the planet wasn't there, it would just keep going on in that direction forever and forever. But the planet right over here, there's an inward force of gravity. We'll talk more about the force of gravity in the future. But this inward force of gravity is going to accelerate this object inwards while it travels. And so after some period of time, this object's velocity vector, if you add the previous velocity with how much it's changed, its new velocity vector, now this is after it's traveled a little bit, its new velocity vector might look something like this. It's traveling at the exact right speed so that the inward force, or so that the force of gravity is always at a right angle to its actual trajectory. It's the exact right speed, so it doesn't go off into deep space, and so it doesn't plummet into the earth. We'll cover that into much more detail. But the simple answer is, unbalanced force on a body will always impact its velocity. It could be its speed, its direction, or both, but it doesn't have to be both. It could be just the speed or just the direction. So this is an incorrect statement. Now the third statement. The reason why initially moving objects tend to come to rest in our everyday life is because they are being acted on by unbalanced forces. This is absolutely true, and this is the example we gave. The reason why if I take an object, if I take my book, and I try to slide it across the desk, the reason why it eventually comes to stop is because we have the unbalanced force of friction, the grinding of the surface of the book with the grinding of the table. If I'm inside of a pool, even if there's absolutely no current in the pool, and if I were to try to push some type of object inside the water, it eventually comes to a stop because of all of the resistance of the water itself. It's providing an unbalanced force in a direction opposite its motion. That is what's slowing it down. So in our everyday life, the reason why we don't see these things go on and on forever is that we have these frictions, these air resistance, or the friction with actual surfaces. And then the last statement, an unbalanced force on an object will always change the object's direction. Well, this one actually is maybe the most intuitive. We always have the situation, if I have let's say I have a block right over here, and it's traveling with some velocity in that direction, 5 meters per second. If I apply an unbalanced force in that same direction, so that's my force right over there. If I apply it in that same direction, I'm just going to accelerate it in that same direction, so I won't necessarily change it. Even if I were to act against it, I might decelerate it, but I won't necessarily change its direction. I could change its direction by doing something like this, but I'm not always necessarily changing the object's direction. So this is not true. An unbalanced force on an object will not always change the object's direction. It can, like these circumstances, but not always. So always is what makes this very, very, very wrong.
Oh, I see. Specific wording here.
Newton's first law tells us that an object at rest will stay at rest, and an object with a constant velocity will keep having that constant velocity unless it's affected by some type of net force. Or you actually could say an object with constant velocity will stay having a constant velocity unless it's affected by net force, because really this takes into consideration the situation where an object is at rest. You could just have a situation where the constant velocity is zero. So Newton's first law, you're going to have your constant velocity. It could be zero. It's going to stay being that constant velocity unless it's affected, unless there's some net force that acts on it. So that leads to the natural question. How does a net force affect the constant velocity, or how does it affect the state of an object? And that's what Newton's second law gives us. So Newton's second law of motion. And this one is maybe the most famous. They're all kind of famous. Actually, I won't pick favorites here, but this one gives us the famous formula: force is equal to mass times acceleration. And acceleration is a vector quantity, and force is a vector quantity. And what it tells us, because we're saying, okay, if you apply force, it might change that constant velocity. But how does it change that constant velocity? Well, let's say I have a brick right here, and it is floating in space. Newton's second law tells us that it's pretty nice for us that the laws of the universe, or at least in the classical sense before Einstein showed up, the laws of the universe actually dealt with pretty simple mathematics. What it tells us is if you apply a net force, let's say on this side of the object, and we talk about net force because if you apply two forces that cancel out and that have zero net force, then the object won't change its constant velocity. If you have a net force applied to one side of this object, then you're going to have a net acceleration going in the same direction. So you're going to have a net acceleration going in the same direction. And what Newton's second law of motion tells us is that acceleration is proportional to the force applied, or the force applied is proportional to that acceleration. And the constant of proportionality, or to figure out what you have to multiply the acceleration by to get the force, and what you have to divide the force by to get the acceleration, is called mass. That is an object's mass. And I'll make a whole video on this. You should not confuse mass with weight. And I'll make a whole video on the difference between mass and weight. Mass is a measure of how much stuff there is. Now that we'll see in the future, there are other things that we don't normally consider stuff that does start to have mass. But for our classical, or at least a first year physics course, you could really just imagine how much stuff there is. Weight, as we'll see in a future video, is how much that stuff is being pulled down by the force of gravity. So weight is a force. Mass is telling you how much stuff there is. And this is really neat that this formula is so simple, because maybe we could have lived in a universe where force is equal to mass squared times acceleration times the square root of acceleration, which would have made all of our math much more complicated. But it's nice. It's just this constant of proportionality right over here. It's just this nice, simple expression. And just to get our feet wet a little bit with computations involving force, mass, and acceleration, let's say that I have a force, and the unit of force is appropriately called the Newton. So let's say I have a force of, I have a force of 10 newtons. And just to be clear, a newton is the same thing. So this is the same thing as 10 kilogram meters per second squared. And that's good that a newton is the same thing as kilogram meters per second squared, because that's exactly what you get on this side of the formula. So let's have a force of 10 newtons, and it is acting on a mass. Let's say that the mass is 2 kilograms, and I want to know the acceleration. And once again, in this video, these are vector quantities. If I have a positive value here, we're going to make the assumption that it's going to the right. If I had a negative value, then it would be going to the left. So implicitly, I'm giving you not only the magnitude of the force, but I'm also giving you the direction. I'm saying it is to the right because it is positive. So what would be the acceleration? Well, we just use F equals ma. You have, on the left-hand side, 10. I could write 10 newtons here, or I could write 10 kilogram meters per second squared. And that is going to be equal to the mass, which is 2 kilograms, times the acceleration, And then to solve for the acceleration, you just divide both sides by 2 kilograms. So let's divide the left by 2 kilograms. Let's divide the right by, or this way. Let's divide the right by 2 kilograms. That cancels out. The 10 and the 2, 10 divided by 2 is, 10 divided by 2 is 5. And then you have kilograms canceling with kilograms. Your left-hand side, you get 5 meters per second squared. And then that's equal to your acceleration. Now, just for fun, what happens if I double? That force? Well, then I have 20 newtons. Well, I'll actually work it out. Then I have 20 kilogram meters per second squared. Kilogram meters per second squared is equal to, and I'll have to color code this, 2 kilograms times the acceleration. Divide both sides by 2 kilograms. And what do we get? Cancels out. 20 divided by 2 is 10. Kilograms cancel with kilograms. And so we have the acceleration in this situation is equal to 10 meters per second squared, is equal to the acceleration. So when we doubled the force, we went from 10 newtons to 20 newtons, the acceleration doubled. Went from 5 meters per second squared and to 10 meters per second squared. So we see that they are directly proportional, and the mass is that how proportional they are. And so you can imagine what happens if we double the mass. If we double the mass in, let's say in this situation, with 20 newtons, then we won't be dividing by 2 kilograms anymore. We'll be dividing by 4 kilograms. And so then we'll have 20 divided by 4, which would be 5 meters per second squared. So if you make the mass larger, if you double it, then your acceleration will be half as much. So the larger the mass you have, the more force you need to accelerate. Or for a given force, the less that it will accelerate, the harder it is to change its constant velocity. I have 4 statements here, and I want you to think about which of these statements are true. And the first statement is an object in motion will slow down unless it is acted on by an unbalanced force in the direction of motion. Interesting. Newton's first law tells us that an object at rest will stay at rest, and an object with a constant velocity. But this one gives us the famous hypothesis: is if you apply the force, as we'll, so let's say I have a force of, so let's say motion. Interesting. Second statement: an object in motion will maintain its speed and direction forever unless acted on by an unbalanced force. Also very interesting. Third statement: an object at rest will stay at rest unless acted on by an unbalanced force. And then the fourth statement: an object acted on by an unbalanced force will always accelerate in the direction of the unbalanced force. So I'll leave you to think about those statements and figure out which of those statements are actually true. It might be nothing.
That kind of makes sense.
None of them, or it might be all of them, or some combination of them. Now let's try to think about each of these statements. So first of all, an object in motion will slow down unless it is acted on by an unbalanced force in the direction of motion. Well, this, at least on a first cut, kind of seems consistent with our everyday experience. If I'm pushing some furniture across the room, so let's say this is the carpet of my house, and I'm pushing a television set. Let's say it's one of those old school heavy television sets. So I'm pushing a television set. The only way that I can keep it in motion is if I keep pushing on it. So let me draw my force of pushing.
Yeah.
My force of pushing. Let's call that right there. The force of Sal pushing the television set. So the only way that I can keep my television set moving, it seems like if I keep applying this pushing force on it. And if I were to stop doing that, it seems like it will slow down. So on a first cut everyday experience, this seems like it would actually maybe be true. It only seems that way because I'm actually not accounting for all of the forces in this situation. There's not just the force of me pushing. There's also the force of friction. There's also the force of friction. So I'll call that. So there is also the force of friction. And if I
Will slow down.
want to keep this TV moving at a constant velocity, my force of pushing, let me make that in vectors, look about the same magnitude. They need to be the same magnitude. If I want to keep my television set at a constant velocity in the direction that I'm pushing, I have to exactly offset the force of friction. If my force of pushing is less than the force of friction, then the TV set will start to decelerate. If my force of pushing is larger than the force of friction, then my TV set will accelerate. But in this scenario right now, I have an object in motion, but there's actually a balanced force. My pushing is completely balanced by the force of friction. Another scenario, if we were to go to deep space, and I'm not even thinking about air resistance right here, but if we were to go into space, where, especially deep space, no planets around, complete vacuum, if an object is in motion, and there are absolutely no forces, balanced or otherwise, there are absolutely no forces acting on it, then that object is going to stay in motion. The only way that it might change its direction or decelerate or accelerate is if there is a net force on it. And just going back to this example, the only reason why it'll slow down if I were to stop pushing is because there is a net force on it, the force of friction. And if you want to think about it, it would probably be a minor amount of air resistance. So this actually isn't true. An object in motion does not have to slow down unless it's acted on by an unbalanced force. An object in motion can stay in motion as long as it's being acted on either by a balanced force or a set of forces that balance each other, or no forces at all. So that is not true. An object in motion will maintain its speed and direction. I have 4 statements here, and I want you to think about which of these statements are true. And the first statement is unless acted on by an unbalanced, or it might be all of them, or each of these statements. So first of all, an object in motion will slow down unless it is acted on by an unbalanced force in the direction of motion. Well, this, at least on a first cut, kind of seems consistent with our everyday experience. If I'm pushing some furniture across the room, so let's say this is the carpet of my house, and I'm pushing a television set. Let's say it's one of those old school heavy television sets. So I'm pushing a television set. The only way that I can keep it in motion is if I keep pushing on it. Let me draw my force of pushing. My force of pushing. Let's call that right there. The force of Sal pushing the television set. So the only way that I can keep my television set moving, it seems like if I keep applying this pushing force on it. And if I were to stop doing that, it seems like it will slow down. So on a first cut everyday experience, this seems like it would actually maybe be true. It only seems that way because I'm actually not accounting for all of the forces in this situation. There's not just the force of me pushing. There's also the force of friction. There's also the force of friction. I'll call that. There's also the force of friction. And if I want to keep this TV moving at a constant velocity, my force of pushing, let me make that the vectors look about the same magnitude. They need to be the same magnitude. If I want to keep my television set at a constant velocity in the direction that I'm pushing, I have to exactly offset the force of friction. If my force of pushing is less than the force of friction, then the TV set will start to decelerate. If my force of pushing is larger than the force of friction, then my TV set will accelerate. But in this scenario right now, I have an object in motion. But the TV set will start to decelerate. If my force of pushing is larger than the force of friction, then my TV set will accelerate. But in this scenario right now, I have an object in motion, but there's actually a balanced force. My pushing is completely balanced by the force of friction. Another scenario, if we were to go into deep space, and I'm not even thinking about air resistance right here, but if we were to go into space, where, especially deep space, no planets around, complete vacuum, if an object is in motion, and there are absolutely no forces, not balanced or otherwise, there are absolutely no forces acting on it, then that object is going to stay in motion. The only way that it might change its direction or decelerate or accelerate is if there is a net force on it. And just going back to this example, the only reason why it'll slow down if I were to stop pushing is because there is a net force on it, the force of friction. And if you want to think about it, it would probably be a minor amount of air resistance. So this actually isn't true. An object in motion does not have to slow down unless it's acted on by an unbalanced force. An object in motion can stay in motion as long as it's being acted on either by a balanced force or a set of forces that balance each other, or no forces at all. So that is not true. An object in motion will maintain its speed and direction forever unless acted on by an unbalanced force. This is true. This is exactly what's happening right over here in the case of a block moving through space in a vacuum.
Maintain its speed.
If there are no forces acting on it, no net forces acting on it, it is not going to change its velocity. Similarly, you could have this situation where you actually have forces acting on it, but they balance each other out. In this situation, as long as I can keep pushing forever and the floor doesn't change and so the friction doesn't change, this thing would keep moving in that direction, theoretically, forever. The only way to change its direction or accelerate it in one direction or another direction would be to have an unbalanced force. So maybe if my force of pushing were larger than the force of friction, or if the force of friction were larger than my force of pushing. So this right over here is absolutely true. Third statement, an object at rest will stay at rest unless acted on by an unbalanced force. And this is actually pretty intuitive, I think, for people. If you just leave something alone, it's just going to stay alone. It's not going to just start spontaneously moving. And so this is true. And it's not just the situation where there's no forces, but it can also be the situation that's going to stay at rest if there are balanced forces acting on it. And so the only way that you can actually get this thing to come out of that rest position is if you have a net force, an unbalanced force. If let's say that this force right here is any amount larger than this force right over here, if they don't completely balance out. So this, once again, is true. Last statement, an object acted on by an unbalanced force will always accelerate in the direction of the unbalanced force.
It's not true.
So if I have an object and there's an unbalanced force, if we net out all the forces, let's say the direction is in, the forces net out and we get a force acting in this direction. This is actually true. The object will always accelerate if it has an unbalanced force acting on it in that direction. It
I mean, you contradict yourself because you said it wasn't true on the first one.
will accelerate if there's a net force in that direction. And there's another way of thinking about
An
it.
object acted on by the unbalanced
If you
force
see
will always
an object that is
accelerate
not
in
accelerating, like my TV that's moving at a constant velocity, or this thing that's just traveling through space. If you see something that is not accelerating, that means that that there must not be an unbalanced force acting on it. You could have balanced forces acting on it, or you could have no forces on it at all, but you can't have an unbalanced force. If you have an unbalanced force, the thing will be accelerating.
Oh,
So let's losing that airplane. It's going at a its state by force impressed. So another way to rephrase what they're saying is that if there's something, everybody persists, so everything will stay at rest or moving with a constant velocity unless it is compelled to change its state by force, unless it's acted on by a force, especially an unbalanced force. And I'll explain that in a second. So if I have something that's at rest, so completely at rest, so I have, this is something that we've seen before. Let's say that I have a rock. Let's say that I have a rock someplace. I have a rock someplace and it's laying on a field of grass. On a field of grass, I can keep observing that rock and it is unlikely to move, assuming that nothing happens to it. If there's no force applied to that rock will just stay there. So the first part is pretty obvious. So everybody persists in a state of being at rest. I'm not going to do the second part, except insofar there's some force being applied to it. So clearly a rock will be at rest unless there's some force applied to it, unless someone here tries to push it or roll it or do something to it. What's less intuitive about the first law is the second part. Everybody persists in either being in a state of rest or moving uniformly straight forward, except insofar as it is compelled to change its state by force impressed. So this Newton's first law, and I think I should do a little aside here, because this right here is Newton. This right here is Newton. And if this is Newton laws, the unbalanced is because you could have two forces that act on something and they might balance out. For example, I could push on this side of the rock with a certain amount of force, and if you push on this side of the rock with the exact same amount of force, the rock won't move. And the only way that it would move if there's a lot more force on one side than on the other side. So if you have an unbalanced force, so if you have a ton of, and maybe the rock is a bad analogy, let's take ice, because ice is easier to move, or ice on ice. So there's ice right here, and then I have another block of ice sitting on top of that ice. So once again, we're familiar with the idea if there's no force acting on it, that ice won't move. But what happens if I'm pushing on the ice with a certain amount of force on that side, and you're pushing on the ice on that side with the same amount of force? The ice will still not move. So this right here, this would be a balanced force, So the only way for the ice to change its condition, to change its restful condition, is if the force is unbalanced. So if we add a little bit of force on this side, so it more than compensates the force pushing it this way, then you're going to see the ice block start to move, start to really accelerate in that direction. But I think this part is obvious. This, something that's at rest will stay at rest unless it's being acted on by an unbalanced force. What's less obvious is the idea that something moving uniformly straight forward, which is another way of saying something having a constant velocity. What he's saying is that something that has a constant velocity will continue to have that constant velocity indefinitely unless it is acted on by an unbalanced force. And that's less intuitive because everything in our human experience, even if I were to push this block of ice, eventually it'll stop. It won't just keep going forever. Even assuming that this ice field is infinitely long, that ice will eventually stop. Or if I throw a tennis ball, that tennis ball will eventually stop. Even if it'll eventually grind to a halt. Or if I roll a bowling ball, or anything we've never seen, at least in our human experience, it looks like everything will eventually stop. So this is a very unintuitive thing to say, that something in motion will just keep going in motion indefinitely. Everything in human intuition says if you want something to keep going in motion, you have to keep putting more force, keep putting more energy into it for it to keep going. Your car won't go forever unless the engine keeps burning fuel and to drive and consuming energy. So what are they talking about? Well, in all of these examples, and I think this is actually a pretty brilliant insight for all of these flows, is that all of these things would have gone on forever. The ball would keep going forever. This ice block would be going on forever, except for the fact that there are unbalanced forces acting on them to stop them. So in the case of ice, even though ice on ice doesn't have a lot of friction, there is some friction between these two. And so you have, in this situation, the force of friction is going to be acting against the direction of the movement of the ice. And friction really comes from at an atomic level. So if you have the actual water molecules in a lattice structure in the ice cube, and then here are the water molecules in the lattice structure
on the ice, on the actual kind of sea of ice that it's traveling on, they do kind of bump and grind into each other. Although they're both smooth, there are imperfections here. They bump and grind. They generate a little bit of heat, and they'll essentially be working against the movement. So there's a force of friction that's being applied to here, and that's why stopping. Not only a force of friction, you also have some air resistance. The ice block is going to be bumping into all sorts of air particles. It might not be noticeable at first, but it's definitely going to keep it from going on forever. Same thing with the ball being tossed to the air. Obviously, at some point, it hits the ground because of gravity, so that's one force acting on it. But even once it hits the ground, it doesn't keep rolling forever, once again, because of the friction. Because of the frictions, especially if there's grass here, the grass is going to stop it from going. And even while it's in the air, it's going to slow down. It's not going to have a constant velocity because you have all of these air particles that are going to bump into it, and exert force to slow it down. So what was really brilliant about these guys is that they could imagine a reality where you didn't have gravity, where you did not have air slowing things down, and they could imagine that in that reality, something would just keep persisting in its motion. And the reason why Galileo, frankly, was probably good at thinking about that is that he studied the orbits of planets. And he could, or at least he's probably theorized, hey, maybe there's no air out there, and maybe that's why these planets can just keep going round and round in orbit, and their speed, because their direction is changing, but their speed never slows down because there's nothing in the space to actually slow down those planets. So anyway, hopefully you found that as fascinating as I do, because on some level it's super duper obvious, but on a whole other level completely not obvious, especially this moving uniformly straight. We're now ready for Newton's third law of motion. And something, once again, you've probably heard people talk about. But in this video, I want to make sure that we really understand what Newton is talking about when he says, and this is a translation of the Latin version of it, to every action, there is always, and just to be clear, Newton was English, but he wrote it in Latin because at that point in time, people wrote things in Latin because it was viewed as a more serious language. But anyway, to every action, there is always an equal and opposite reaction, or the forces of two bodies on each other are always equal and are directed in opposite directions. So what Newton is saying is that you can't just have a force acting on some object without that object also having an opposite force acting on the thing that's trying to act on it. And just to make it clear, let's say that we have and we'll talk about these examples in a second. Let's say that I have some type of block right over here, and that I move and I press on the block and I try to push it forward. So this is my hand. This is my hand trying to press on the block and exert a force, a net force in that direction, so that the block moves to the right. Maybe this block is sitting on some type of ice so that it can move. So let's say that I have some that doesn't look like ice, do a more ice-like color. So the block is sitting on maybe some ice like that. So Newton's third law saying, look, I can press on this block, and sure, I'll exert a net force on this block, and that net force will accelerate the block, assuming that I can overcome friction. And if it's on ice, I can do that. But that block is going to exert an equal and opposite force on me. An equal and opposite force on me. And for direct evidence, this is something, even though it might not be so intuitive when it's said, this equal and opposite force, but direct evidence that it's exerting an equal and opposite force is that my hand will get compressed. I can actually feel the block exerting pressure on me. Take your hand right now and push it against your desk or whatever you have nearby, and you are clearly exerting a force on the desk. So let me draw. So let's say I have a desk right here, and if I try to push on the desk, so once again, that's my hand right here pushing on the desk. If I push on the desk, and I'm actually doing it right now while I record this video, you'll see, so I'm clearly exerting a force on the desk. If I do it hard enough, I might even get the desk to shake or tilt a little bit. I'm actually doing that right now. But at the same time, you'll see that your hand is getting compressed. The palm of your hand is being pressed down. And that's because the desk is exerting an equal and opposite force on you. If it wasn't, you actually wouldn't even feel it because you wouldn't even feel the pressure. Your hand would be completely uncompressed. Another example of that, say you're walking in the beach. Say you're walking on the beach and you have some sand right here. If you were to step on the sand, so let's say that this is your shoe, do my best attempt to draw a shoe. So this is the shoe. If you were to step on the sand, clearly you are exerting a force on the sand. You are exerting a force on the sand. The force that you're exerting on the sand is the force of your weight, the gravitational attraction between you and the earth. You're exerting that on the sand. The sand is also, and another evidence of that is that the sand is going to be displaced. You're going to create a footprint. The sand is going to move out of the way because it's being pushed down so hard. So clearly you are exerting a force on the sand. But the sand is also exerting an equal and opposite force on you. Is also exerting an equal and opposite force on you. And what's the evidence of that? Well, if you believe Newton's second law, if you have this gravitational force on you, you should be accelerating downwards unless there is some other force that balances it out. And the force that balances it out is the force that the beach or the sand is exerting on you upwards. And so when you net them out, there's a zero net force on you. And that's why you get to stay there, why you don't start accelerating down towards the center of the earth. Other examples of this is maybe the most famous example of Newton's third law, is just how rockets work. when you're in a rocket, either trying to escape the atmosphere or maybe you're in space, there's nothing to push off of, nothing to push off that let you accelerate. So what you do is you keep stuff to push off in your fuel tanks. And when you allow the proper chemical reactions or the proper combustion to take place, what it does is it expels gases at ultra high velocities out the back of your rockets. And each of those particles, you're exerting a force on them, enough force, even though they're super small mass for each of them, they're going at super high velocity, so they're being accelerated tremendously. So there's an equal and opposite force on the rocket, the thing that is actually expelling the gas. And so that's what allows a rocket to accelerate, even when there's nothing in this direct vicinity to push off of. It just expels a bunch of things, or accelerates a bunch of things at a super fast rate. It exerts a force on all these particles, and that allows an equal and opposite force to accelerate the rocket ahead. And another example of this is if you ever find yourself drifting in space, and this is an actual useful example so that you don't end up drifting in space forever. Let's say we don't ever want this to happen. This astronaut, by some chance, he loses his connection to this little tool arm right here in the space shuttle, and he starts drifting away. He starts drifting away. What can that astronaut do to change the direction of his motion so that he drifts back to the space shuttle? Well, you look around, you're like, wow, there's nothing to push off of. He doesn't have any wall to push off of. And let's just assume he doesn't have any rocket jets or anything like that. What could he do? Well, the one thing you could do, and this is the situation, if you're ever drifting in space, is you should find the heaviest, or I should say the most massive thing on you, and we'll explain the difference between mass and weight in a future video, but you should find the most massive thing that you can carry, that you can take off of you, that you can throw, and you should throw it in a direction opposite yourself. So let me put it this way. If I throw, let's say I'm in space and I'm floating, I'll make it look like the glove of a, so let's say that this is the glove of the astronaut. There you go, that's his hand. That's the astronaut's hand right over here. And let's say he finds some piece of equipment on his, or she finds some piece of equipment on them that they can throw. They can take off of their tool set, and they can find the most massive object that they can throw. So what's going to happen is, for some period of time, while they push this object away, they will be exerting a force on that object. They will be exerting a force on that object for some period of time while they have contact with the object. And that entire time, that object, while it is accelerating, while the astronaut is exerting a force on it, will be exerting an equal and opposite force on the hand of the astronaut, or on the astronaut itself. So the object will accelerate in that direction, and while the astronaut is pushing, the astronaut will accelerate in this direction. So what you do is you throw the opposite direction, and that'll allow the astronaut to accelerate towards the space shuttle and hopefully grab onto something.
Renee, I will now do a presentation on the center of mass. And the center of mass, hopefully, is something that will be a little bit intuitive to you and actually has some very neat applications. So, in very simple terms, the center of mass is a point. Let me draw an object. Let's say that this is my object. It's a ruler. And so this ruler, it exists, so it has some mass. And my question to you is, what is the center of mass? You say, Sal, well, in order to figure out the center of mass, you have to tell me what the center of mass is. And what I tell you is the center of mass is a point. And it actually doesn't have to even be a point in the object. And I'll do an example soon where it won't be. But it's a point, and at that point, for dealing with this object as a whole, or the mass of the object as a whole, we can pretend that the entire mass exists at that point. And what do I mean by saying that? Well, let's say that the center of mass is here. And I'll tell you why I picked this point, because that is pretty close to where the center of mass will be. If the center of mass is there, and let's say that the mass of this entire ruler is, I don't know, 10 kilograms. This ruler, if a force is applied at the center of mass, let's say 10 newtons, right? So the mass of the whole ruler is 10 kilograms. 10 kilograms. If a force is applied at the center of mass, this ruler will accelerate the same exact way as would a point mass. Let's say that we had just had a little dot. But that little dot had the same mass, 10 kilograms. And we were to push on that dot 10 newtons. In either case, in the case of the ruler, we would accelerate upwards at what? Force divided by mass. So we would accelerate upwards at 1 meter per second squared. And in this case of this point mass, we would accelerate that point. When I say point mass, I'm just saying like something really, really small, but it has a mass of 10 kilograms. So it's much smaller, but it has the same mass as this ruler. This would also accelerate upwards with a magnitude of 1 meter per second squared. So why is this useful to us? Well, sometimes we have some really crazy objects, and we want to figure out exactly what it does. And if we know its center of mass first, we can know how that object will behave without having to worry about the shape of the object. And I'll give you a really easy way of realizing where the center of mass is. If the object has a uniform distribution, when I say that, it means, let's say, for simple purposes, if it's made out of the same thing, and that thing that it's made out of, its density doesn't really change throughout the object, the center of mass will be the object's it's a geometric center. So in this case, this is all, ruler is almost a one-dimensional object. We just went halfway, the distance from here to here, the distance from here to here, same as the center of mass. If we had a two-dimensional object, let's say we had like this triangle, and we wanted to figure out its center of mass, it'll be the center in 2 dimensions. So it'll be something like that. Now, if I had another situation, let's say I had let's say that I have this square. I don't know if that's thick enough for you to see. You can draw it a bit thicker. Let's say I have the square. But let's say that half of the square is made from, let me see. Half of the square, let's say this half of the square, is made from lead. Let's say this half is made from lead. And let's say the other half of the square, I don't know, it's made from something lighter than lead. It's made of styrofoam. That is lighter than lead. So in this situation, the center of mass isn't going to be the geographic center. I don't know how much denser lead is than styrofoam, but the center of mass is going to be someplace closer to the right, because this object does not have a uniform density. And it'll actually depend on how much denser the lead is than styrofoam, which I don't know. But hopefully that gives you a little intuition of what the center of mass is. And now I'll tell you something a little more interesting. Every problem we have done so far, now that object will behave without, in either case, with a magnitude of 1 meter per second squared. So why is this useful to us? Well, sometimes we have some really crazy objects, and we want to figure out exactly what it does. And if we know its center of mass first, we can know how that object will behave without having to worry about the shape of the object. And I'll give you a really easy way of realizing where the center of mass is. If the object has a uniform distribution, when I say that, I mean, let's say, for simple purposes, if it's made out of the same thing, and that thing that it's made out of, its density doesn't really change throughout the object, the center of mass will be the object's it's a geometric center. So in this case, this is all, ruler is almost a one-dimensional object. We just went halfway, the distance from here to here, the distance from here to here, same as the center of mass. If we had a two-dimensional object, let's say we have like this triangle, and we want to figure out its center of mass, it'll be the center in 2 dimensions. So it'll be something like that. Now, if I had another situation, let's say I had let's say that I have this square. I don't know if that's thick enough for you to see. Let me draw it thicker. Let's say I have the square. But let's say that half of the square is made from, let me see. Half of the square, let's say this half of the square, is made from lead. So this half is made from lead. And let's say the other half of the square, I don't know, it's made from something lighter than lead. It's made of styrofoam. That is lighter than lead. So in this situation, the center of mass isn't going to be the geographic center. I don't know how much denser lead is in styrofoam, but the center of mass is going to be someplace closer to the right, because this object does not have a uniform density. And it'll actually depend on how much denser the lead is in styrofoam, which I don't know. But hopefully that gives you a little information of what the center of mass is. And now I'll tell you something a little more interesting. Every problem we have done so far, we actually made the simplifying assumption that the force acts in the center of mass. So if I have an object, let's say the object looks like a horse. Let's say that object, if this is the object's center of mass, I don't know where the horse's center of mass normally is, but let's say the horse's center of mass is here. If I apply force directly on that center of mass, if I apply force directly at that center of mass, then the object will move in the direction of that force with the appropriate acceleration. I mean, we can divide the force by the mass of the entire horse, and we figure out the acceleration in that direction. But now I'll throw in a twist. And actually, every problem we did, all these Newton's laws problems, we assumed that force acted at the center of mass. But something more interesting happens if the force acts away from the center of mass. Let me see. Let me take that ruler example. I don't know how you would do the horse. If I have this ruler again, and this is the center of mass, as we said, any force that we act on the center of mass, the whole object will move in the direction of the force. It'll be shifted by the force, essentially. But now this is what's interesting. If that's the center of mass, and if I were to apply force someplace else, away from the center of mass, let's say I apply a force here, I want you to think about for a second what will probably happen to the object.
I mean, I think it's going to move relative to the point. It's going to shift that object up, right? It's just that object will section of the object.
Turns out that the object will rotate. And so think about we're on a space shuttle or we're in deep space or something, and I have a ruler, and if I just push at one end of the ruler, what's going to happen? Am I just going to push the whole ruler, or is the whole ruler going to rotate? And hopefully, I want you to think about for a second what will probably happen to the object. Well, it turns out that the object will rotate.
If you're pushing here, which direction? Just completely straight? If you're completely straight, then the ruler is going to shift 90 degrees. 90 degrees? 90 degrees? Yes, 90 degrees counterclockwise. 90 degrees counterclockwise, 180 counterclockwise. Oh, wait. 90 degrees counterclockwise.
Okay. And so think about we're on a space shuttle or we're in deep space or something, and if I have a ruler, and if I just push at one end of the ruler, what's going to happen? Am I just going to push the whole ruler, or is the whole ruler going to rotate? And hopefully your intuition is correct. The whole ruler will rotate around the center of mass.
What? Oh, okay. Well, I mean, you're pushing at some angled force. I'm sure.
In general, if you were to throw a monkey wrench at someone, and I don't recommend that you do, but if you did, and while the monkey wrench is spinning in the air, it's spinning around its center of mass. Same for a knife. That if you're a knife catcher, that's something you should think about. That the object, when it's in a when it's free, when it's not fixed at any point, it rotates around the center of mass. That's very interesting. So you can actually throw random objects, and that point at which it rotates around, that's the object's center of mass. That's an experiment that you should do in an open field around no one else. Now, with all of this, and I'll actually in the next video tell you what this is when you have a force that causes rotational motion as opposed to a shifting motion. That's more cool in the next video. But now I'll show you just a cool example of how the center of mass is relevant in everyday applications like high jumping. So in general, let's say that this is a bar. This is a side view of the bar, right? This is a big wooden bar, and a guy wants to jump over the bar.
This is a what?
It's like high jumping. So in general, let's say that this is a bar. This is a side view of the bar, right? This is a big wooden bar, and a guy wants to jump over the bar. His center of mass is, people's center of mass is around their gut. I think how the center of mass is relevant in everyday applications like high jumping. So in general, we say that this is a bar.
What is high jumping? Who's this? Oh, okay, high jumping. Okay. Shoot, what was it?
Side view of the bar, right? This is a big wooden bar, and a guy wants to jump over the bar. His center of mass is, people's center of mass is around their gut. I think evolutionarily, that's why our gut is there, because it's close to our center of mass. So there's two ways to jump. You could just jump straight over the bar, kind of like a hurdle jump, in which case your center of mass would have to, cross over the bar, and we could figure out this mass, and we can figure out how much energy and how much force is required to propel a mass that high, because we know projectile motion, and we know all of these laws. But what you see a lot in the Olympics is people doing a very strange type of jump. where when they're going over the bar, they look something like this. Their backs are arched over the bar. That's not a good picture. But what happens when someone arches their back over the bar like this? Hope you get the point. This is the bar right here. Well, it's interesting. When if you took the average of this person's density and figure out its geometric center and all of that, the center of mass in this situation, if someone jumps like that, actually travels below the bar. Because the person arches their back so much, if you took the average of the total mass of where the person is, their center of mass actually goes below the bar. And because of that, you can clear a bar without having your center of mass go as high as the bar. And so you need less force to do it. Or another way to do it, another way to say it, with the same force, you could clear a higher bar. Hopefully I didn't confuse you, but that's exactly why these high jumpers arch their back so that their center of mass is actually below the bar and they don't have to exert as much force. Anyway, hopefully you found that to be a vaguely useful introduction to the center of mass. And I'll see you in the next video on torque.
If you bend your body, more of your body mass will be behind you. Wow. Yeah, okay. We're gonna have to see that. Actually, let me read this real quick. Ooh, okay. Okay, yeah. Okay. Center mass is below the bar. Center mass is below the bar, and that's what allows the jumper to jump higher. Let's see. Yeah, we'll stop today at fluids at rest. We're completing fluids at rest now. Then I have to do Anki. We should be more.
Welcome to the presentation on torque. So if you watched the presentation on the center of mass, which you should have, you might have had a little bit of a glancing view of what torque is, and now we'll go into more detail. So in general, from the center of mass video, we learned that this is a ruler, this is the ruler center of mass, and if I were to apply a force at the center, mass, I would just shift the whole ruler in the, or I would accelerate the whole ruler in the direction of the force. So I was applying it to the center of mass there. The whole ruler would accelerate in that direction, and we figure it out by taking the force that we're applying to mass. And in that center of mass video, I implied, well, what happens if the
Right.
force is applied here, away from the center of mass. Well, in this situation, the object, assuming it's a free floating object, it's on a space shuttle or something, it will rotate around the center of mass. And that's also true if we didn't use the center of mass, but instead we fixed the point. So let's say we had, let's say, here's another ruler that's less height than the previous one. Instead of worrying about its center of mass, let's say that it's just fixed at a point here.
Um, so I think okay, I think
It's fixed here, so it's like, I don't know. This could be like the hand of a clock, and it's nailed down to the back of the clock right there. So if we were to didn't use the center of mass, but instead we fixed the point. So let's say we had, let's say, here's another ruler that has less height than the previous one. Instead of worrying about its center of mass, let's say that it's just fixed at a point here. Let's say it's fixed here, so it's like, I don't know. This could be like the hand of a clock, and it's nailed down to the back of the clock right there. So if we were to try to rotate it, it would always rotate around this point. And the same thing would happen. If I were to apply a force at this point, maybe I could break the nail off the back of the clock or something, but I won't rotate this needle or this ruler or whatever you want to call it. But if I were to apply a force here, I would rotate the ruler around the pivot point. And this force that's applied a distance away from the pivot point, or we could say from the axis of rotation or the center of mass, that's called torque. And torque, the letter for torque, is this Greek, I think that's tau. It's a curvy T. And torque is defined as force times distance. And what force and what distance is it? It's the force that's perpendicular to the object. I guess you could say to the distance vector, right? If this is the distance vector, let me do it in a different color. If this is the distance vector, the force is going to be the component of the force is perpendicular to this distance vector. And this is torque. And so what are its units? Well, force is newtons and distance is meters. So this is Newton meters. And you're saying, hey, Sal, newtons times meters, force times distance, that looks an awful lot like work. And it's very important to realize that this isn't work, and that's why we won't call this joules. Because in work, what are we doing? We are translating an object. If this is an object, and I'm applying a force, I'm taking the force over a distance that's in the same direction as the force, right? Here, the distance and the force are parallel to each other. You can say the distance vector and the force vector are in the same direction. In this situation, and of course that's translational, the whole object is just moving, it's not rotating or anything. In the situation of torque, let me switch colors. The distance vector, this is the distance from the fulcrum or the pivot point of the center of mass to where I'm applying the force. This distance vector is perpendicular to the force that's being applied. So torque and work are fundamentally two different things, even though their units are the same. And just as a little bit of notational, this distance is often called the moment arm distance. And I don't know where that came from. Maybe one of y'all can write me a message saying where it did come from. And often in some of your physics class, they'll didn't call torque as a moment. But we'll deal with the term torque, and that's more fun because eventually we can understand concepts like torque horsepower in cars. So let's do a little bit of math. Hopefully I give you a little bit of intuition. So let's say I had this ruler, and let's say that this is its pivot point right here. Right, so it'll rotate around that point. It's nailed to the wall or something. And let's say that I apply a force, let's say the moment arm distance. So let's say that this distance, I'll do a different color. Let's say that this distance right here is 10 meters. And I would apply a force of 5 newtons, perpendicular to the distance vector, or to the dimension of the moment arm. You can do it either way. So torque is pretty easy in this situation. Torque is going to be equal to the force, 5 newtons, times the distance, 10. So it'll be 50 newton meters. And you're probably saying, well, Sal, how do I know if this torque is going to be positive or negative? And this is where there's just a general arbitrary convention in physics, and it's good to know. If you are rotating clockwise, torque is negative. Well, let me go the other way. If you're rotating counterclockwise, like we were in this example, right? We're rotating counterclockwise, the opposite direction of which a clock would move in. Torque is positive. And if you rotate clockwise, the other way, torque is negative. So clockwise is negative. And I'm not going to go into the whole physics, the whole cross product and the linear algebra of torque right now, because I think that's a little bit beyond the scope. But we'll do that once we do more mathematically intensive physics. But so good enough, there's a torque of 50 newton meters, and that's all of the torque that's acting on this object. So it's going to rotate in this direction, and we don't have the tools yet to figure out, I guess, how quickly will it rotate. But we know it'll rotate, and that's vaguely useful. But what if I said that the object is not rotating, and that I have another force acting here, and let's say that force is, I don't know, let me make up something. That's 5 meters to the left of the pivot point. This is 5 meters to the left of the pivot point. And if I were to tell you that that this object does not rotate, so if I tell you that the object is not rotating, that means the net torque on this ruler, it must be 0, because it's not, well, its rate of change of rotation is not changing. I should be a little exact. If I'm applying some force here and still not rotating, then we know that the net torque on this object is 0. So what is the force being applied here? Well, what is the net torque? Well, it's this torque, which we already figured out, and it's going in the clockwise direction. So it's 5, brighter color, 5 times 10. And then the net torque, the sum of all the torques have to be equal to 0. So what's this torque? So let's call this F. This is a force. So plus, well, is this force is acting in what direction? Clockwise or counterclockwise?
Clockwise. So it's negative?
Well, it's acting in the clockwise direction, right? This force wants to make the ruler rotate this way. So this is actually going to be a negative torque. So let's say a negative number here times F times its moment arm distance, so times 5. And all of this has to equal 0. The net torque is 0 because the object, its rate of change of rotation isn't changing, or if it started off not rotating, it's still not rotating. So here we get 50 minus 5F is equal to 0. 50 is equal to 5F. F is equal to 10. And if we follow the units all the way through, we get that F is equal to 10 newtons. So that's interesting. I applied double the force at half the distance and offsetted half the force at twice the distance. And this should all connect or start to connect with what we talked about with mechanical advantage, right? You could view it the other way. If let's say these are people applying these forces, this guy over here, he's applying 10 newtons. He's much stronger. He's twice as strong as this guy over here, but because this guy is twice as far away from the pivot point, he balances the other guy. So you can kind of view it as this guy having some mechanical advantage or having a mechanical advantage of two. And watch the mechanical advantage videos if that confuses you. But this is where torque is useful, because if an object's rate of rotation is not changing, you know that the net torque on that object is zero, and then you can solve for the forces or the distances. I'm about to run out of time, so I will see you in the next video.
Sure. Let's see. Distance, speed. The object with zero acceleration and the object having constant acceleration to the same states. To its high initial speed. That's a good question. Wow, these are good. What is significant is its high initial speed. To its high initial speed. Remains at rest. Or maintains uniform motion. Maintains its uniform motion unless acted upon by an external force. By an external force. Is that the same thing? Oh, maybe. See. Okay. Let's see. So this. All right, I'm gonna take a 10-minute break here. I need to go outside. Get some air. Ah! MCAT. Yeah. I need to actually also review Need to review acceleration real quick. Actually, after this one, we'll review acceleration. I need to get to 9, right? 3, 6. No. Kinetic movement. To be honest with you, I actually want to go back and just finish up. I want to finish up the rest of it. Maybe that kind of makes sense to do. I don't like kind of this half kind of thing. Anyways, okay, I'll be back.
It's so funny.
You're cut off.
Glasses are
Cut off. You're done. You're cut off. You're done. I can't believe you did that. I can't believe you did
Your
that.
glasses were dropped. That was so funny, right?
You're such a jerk.
Oh my god.
Let me get some ice and
Babe,
get some milk.
I got 4.
You got 4. Let's leave at 9 then. We're
Sure.
leaving 9.
Sure. I don't have a problem with that.
Okay.
Oh my god, Amy. Do you have a mosquito medicine?
No,
No?
I don't know what that is.
It's like you get it when you have you got bit.
Can you turn my phone? No, sorry, baby. I never really get bit.
Oh,
I think I have something wrong with me because the mosquitoes don't want my blood.
can I get one? Thank you.
Yeah.
2, thank you.
Actually, go for it. I think we can
3, thank you.
go for it.
Oh, you have another charger? Because this is for the back.
Oh, just put my phone there then.
Sure.
You charge it from there. Mm-hmm. Uh-huh.
Oh, baby.
All right. What happened? Come on. Weird. Oh, yeah. You know the physics?
Something. No, some part.
What do you think?
For the B. Oh, what? Wait. 0 acceleration. No. It's C.
Yeah, I was thinking C as well. Good job.
Thank you.
What is it?
I don't know. I don't know what the vector are.
I think D. Ah.
C. No.
Huh?
Uh-oh.
I'm not too sure about this one.
Uh-oh.
Uh-oh. Forget it, go.
Oh.
Wow. I don't know. I can't do it in my head. What? Oh, maybe I did wrong. Did I? I got 188.
What?
I don't know. Let's go.
Oh. What's up?
Oh, so good.
What's the answer?
I think it's the balance. It's double balance. A equals 0. F equals 0. Oops. F mat. So I don't think it's this one then, huh?
I think it's. What's your take?
In a straight line away. I think maybe this one makes sense.
Which one? A?
Maybe A.
Okay. Oh, my take is B.
Maybe B. Why? Oh, because what does that mean? So you slow down when you change directions, then you have to speed up to maintain that speed. Is that why or what? Why did you think it was B?
I was weighing between A and B,
Oh, but why B though?
and it was wrong.
It just be because A was wrong.
The C and D doesn't make sense, right?
Yeah. Okay. Next.
What? You don't understand it. You don't understand it. Why you want to go next?
Go back up. What is it? Oh. Oh, because this one came in. So because it changed direction, it must then accelerate. Because a change in direction must mean that you have an acceleration.
Yeah. Okay.
Okay. That's really good, by the way.
Right. You want this one? This is like.
Action prepare. Action reaction. Oh, okay. I think we're talking about Newton's third law.
Nine and 8. 9 and 8.
Okay. Yeah. I don't think so.
Hey, somebody else. Somebody else.
Oh, the flags? Oh. um. Yeah. Why not?
Another why not?
Why not? This one says the best.
Oh, really? The pencils?
Yeah.
Why? Look at the extra purple.
That's okay. That's 2 minutes. I'm okay. I'm not gonna eat too much more.
Why?
I didn't lose weight.
Okay.
Wow. I don't think it makes any sense. Normal force of the table. Force. Or maybe it is A.
Wait.
I don't know. Maybe.
Yeah.
Yeah, I think D or B. Forces are of the same type or contact
Oh.
and that act on different objects. Oh. Where the field force and normal force is a contract force. Okay. Oh. I'm pretty sure. Maybe. The resultant force of the convertible. Oh, the resultant force of the convertible. Really? I would not think so.
120 meters. This she has been displayed. .60. This is probably cancel out. You can do the same thing with units. And then we see the meter. You need a runway. This leaves us with meters. So you need a runway of 3,000, over 3,000 meters for one of these suckers to take. Like this. We were able to figure out that we were able to get the last thing I want to introduce. There's 39. For three, like 1.8. Actually, let me. Second. So you have 13 plus 5, 18. You divide that by 2. Your average velocity is 9 meters per second, which is the average velocity of your eye. Equal 1.
Hear the terms balanced forces and unbalanced forces a lot when you're dealing with physics. And what I want to do in this video is give you a bunch of scenarios and have you think about whether the forces in these scenarios are balanced or unbalanced. So let's start with the scenario where we have the ground, and then sitting on the ground we have a rock. Now, the force of gravity is going to be pulling the rock downwards towards the center of the earth. And it's going to be pulling it, it's essentially the weight of the rock. It's going to be pulling it downwards, let's say at a force of 5 newtons downwards. But then the rock is also being supported by the ground. The ground is keeping it from being plummeted downwards. So the ground is providing an upwards force or normal force in this situation. The ground is providing a normal force, I'll do it in green. The ground is providing a normal force in this situation of 5 newtons. So these forces have the same magnitude, but they're going in opposite directions. So that is the first scenario. Now let's think about another scenario. So I'll draw the rock again. So I'll draw that same rock. So now I will draw that same rock. We'll assume it's the same rock. The force of gravity is still downwards, 5 newtons. 5 newtons downwards. And there's still a normal force, the ground supporting the rock, of 5 newtons upwards. 5 newtons upwards. 5 newtons upwards. And now there's some character who's trying to push the rock. So we have some character here, and he is trying to push the rock, and he's applying a force of 2 newtons to the right. But then there is a force of friction between the rock and the ground that is going I'll do friction in orange, 2 newtons to the left. 2 newtons to the left. So that right over there is the force of friction is going against that guy's pushing. Now let's do another scenario. Once again, very similar scenario. So let's draw another scenario where I have a rock now. I have maybe the same rock. And here I have a 5 newton force downwards, force of gravity, like the rest of the scenarios. And I have normal force, the rock is being supported by the ground, 5 newtons upwards. And this guy now here has been able to push a little bit harder. He's pushing a little bit harder. He really put his back into it. And now he's pushing with a force of 3 newtons to the right. And the force of friction is still 2 newtons to the left. So that right over there is the force of friction. Now let's do a couple more scenarios. Now let's just imagine that this is the ground. That's the ground. And then I have the rock. The rock is not resting on the ground. And so the only force I have acting on the rock right now is the force of gravity acting downward. We're assuming we're not going to think too much about. Actually, let's think about it. Let's put it. So I have the force of gravity. There's 5 newtons down. But I have some air resistance here. You can do this, a force of friction of the air. And that is, let's say that is 1 newton up. 1 newton up. This is the force of friction, or you can call it air resistance. Air resistance. All as the thing bumps into all of the air particles as it is falling to the ground. And then the last scenario, I'll draw the rock again, because that seems to be the theme for this video. The last scenario, that's the ground. The rock is resting on the ground. The rock is green. The rock is brown. The rock is resting on the ground. And I have the force of gravity, 5 newtons downwards. So 5 newtons towards the center of the earth. The rock is being supported by the ground, 5 newtons upwards. 5 newtons upwards. And now this guy is pushing really hard. So this guy right over here is pushing really hard. And so he's applying, let's make that 4 newtons. 4 newtons in that direction. You have 2 newtons from the force of friction. I won't draw that just yet. And you also have another character right over here who's trying to keep this guy from pushing the block. So he's pushing in the other direction at 1 newton. So you have 2 newtons of the force of friction. You have this guy pushing 1 newton against this guy's motion to the left. So between this guy and the force of friction, you have 3 newtons. You have 3 newtons going in that direction. So now I'll let you think about which of these have an unbalanced force in them, or which of these have a net force going on. So let's look at the first scenario. We have a 5 newtons force of gravity acting towards the center of the earth, 5 newton normal force of the ground supporting the block. These have the same magnitude in the exact opposite direction, so they cancel out. These forces completely balance each other out. There is 0 net force going on. There are no forces we have going on in the horizontal direction. So you have 0 net force. These right here are balanced, right? We would not consider this one of the scenarios where we see an unbalanced force. Let's go over here. Once again, this 5 newtons and that 5 newtons, they are balancing each other. And then in the horizontal direction, this guy's pushing of 2 newtons to the right is to be completely balanced by the force of friction of 2 newtons to the left. And because they're balanced, you're going to have no net force actually blocking it's equipped to accelerate. So once again, these are all balanced forces, where there's no unbalanced or net force going on right over here. In this scenario, once again, in the vertical direction, these forces are balanced. The normal force in this scenario is balancing the force of gravity, keeping the rock from plummeting, from accelerating towards the center of the earth. And you do have 2 forces that are counteracting in the horizontal direction. This guy's pushing harder with 3 newtons, but the force of friction now is only 2 newtons to the left. So you do have a net force to the right. 3 newtons to the right, 2 newtons to the left. You have a net force. You have a net force of 1 newton, to 1 newton to the right. Or you see it's right based on how I do the vector. So you do have a net force, or another way of thinking about it, that this is a scenario where you have unbalanced forces, in particular in the right-left direction. Now let's look at this over here. We only have forces the way I described it, acting in this vertical direction. You have the force of gravity, 5 newtons downwards. You have a counteracting force, the force of air resistance, 1 newton upward, but they don't completely balance out. You still have a net force. You still have a net force of 4 newtons downwards. And so this is an unbalanced situation. Then finally, right over here, we're sitting on the ground in the vertical direction. Normal force counteracting the force of gravity, those are balanced. But then in the horizontal direction, this guy to the right, we have more force, 4 newtons, it'll be halfway to the left. 3 newtons is this guy plus the force of friction. So in this situation, you do have a net force in the rightward direction. Once again, a 1 newton force to the right, a 1 newton net force. This is an unbalanced. This is a scenario where we have unbalanced forces. Say that I have a huge, maybe frozen over lake, smooth surface of ice over here. My best attempt to draw a flat surface of ice. And I'm going to put 2 blocks of ice here. So I'm going to put 1 block of ice just like this, 1 block of ice right over here. And I'm going to put another block of ice right over here, and another block of ice right over here. And these blocks of ice are identical. They're both 5 kilograms. They are both 5 kilograms. Let me write this down. So they are both 5 kilograms, or they're both of their masses, I should say, are 5 kilograms. And the only difference between the two is that relative to the pond, this one is stationary, this one is stationary, and this one is moving with a constant velocity. Constant velocity in the rightwards direction. And let's say that its constant velocity is at 5 meters per second. 5 meters per second. And the whole reason why I made blocks of ice on top of ice is we're going to assume, at least for the sake of this video, that friction is negligible. Now, what does Newton's first law of motion tell us about something that is either not in motion, or you could use has a constant velocity of 0, or something that has a constant velocity? Well, Newton's first law says, well, look, they're either going to keep their constant velocity or stay stationary, which is constant velocity 0, unless there is some unbalanced 5 kilograms, or both of their masses, I should say, are 5 kilograms. And the only difference between the two is that relative to the pond, this one is stationary, and this one is moving with a constant velocity. Constant velocity in the rightwards direction. And let's say that its constant velocity is at 5 meters per second. 5 meters per second.
And the whole reason why I made blocks of ice on top of ice is we're going to assume, at least for the sake of this video, that friction is negligible. Now, what does Newton's first law of motion tell us about something that is either not in motion, or you could do this as a constant velocity of 0, or something that has a constant velocity? Well, Newton's first law says, well, look, they're going to be at they're going to keep their constant velocity or stay stationary, which is constant velocity of 0, unless there is some unbalance, unless there is some net force acting on an object. So let's just think about it here. In either of these situations, there must not be any unbalanced force acting on it, or there must not be any net force. But if you think about it, if we're assuming that these things are on Earth, there is a net force acting on both of them. Both of them are at the surface of the Earth, and they both have mass. So there will be the force of gravity acting downwards on both of them. There's going to be the downward force of gravity on both of these blocks of ice, and that downward force of gravity, the force of gravity, is going to be equal to the gravitational field of near the surface of the Earth times, which is a vector, times the mass of the object. So times 5 kilograms. 5 kilograms. This right over here is 9.8 meters per second squared. So you multiply that times 5, you get 49 kilogram meter per second squared, which is the same thing as 49 newtons. So this is a little bit of a conundrum here. Newton's first law says an object at rest will stay at rest, or an object at motion will stay in motion, unless there's some unbalanced or unless there's some net force. But based on what we've drawn right here, it looks like there's some type of a net force. It looks like I have 49 newtons of force pulling this thing downwards. But you say, no, Sal. Obviously this thing won't start accelerating downwards because there's ice here. It's resting on a big pool of frozen water. And so my answer to you is, well, if that's your answer, then what is the resulting force that cancels out with gravity to keep these blocks of ice, either one of them, from plummeting down to the core of the Earth, from falling, or from essentially going into free fall or accelerating towards the center of the Earth? And you say, well, I guess if these things would be falling, if not for the ice must be providing the counteracting force. And you are absolutely correct. The ice is providing the counteracting force in the opposite direction. So the exact magnitude of force, and it is in the opposite direction. And so if the force of gravity on each of these blocks of ice are 49 newtons downward, is completely netted off by the force of the ice on the block upwards. And that will be a force of 49 newtons upwards in either case. And now, hopefully, it makes sense that Newton's first law still holds. We have no net force on this in the vertical direction. Actually, no net force on this in either direction. That's why they have a constant velocity. This guy has a 0 velocity in the horizontal direction. This guy has a constant velocity in the horizontal direction. And neither of them are accelerating in the vertical direction, because you have the force of the ice on the block, the ice supporting the block, that's completely counteracting gravity. And this force in this example is called the normal force. This is the normal force. It's 49 newtons upwards. This right here is the normal force. And we'll talk more about the normal force in future videos. The normal force is the force when anything is resting on any surface is perpendicular to that surface. It's going to start to matter a lot when we start thinking about friction and all the rest. So what we'll see in future videos, when you have something on an incline, and let's say I have a block on an incline like this, the normal force from the, this wedge on the block is going to be perpendicular. To the surface. And if you really think about what's happening here, it's fundamentally an electromagnetic force. Because if you really zoomed in on the molecules of the ice, right over here, even better, the atoms of the ice here, you really zoomed in on the atoms or the molecules of the ice up here, what's keeping this top block of ice from falling down is that in order for it to go through, its molecules would have to kind of compress against, or I guess would have to get closer to the water molecules or the individual atoms in this ice down here. And the atoms, let me draw it at an atomic level right over here. So maybe let me draw one of this guy's molecules. So you have an oxygen with 2 hydrogens. You have an oxygen with 2 hydrogens. It forms this big lattice structure, and we can talk about more of that in the chemistry playlist. And let's talk about this ice as one of these molecules. So maybe it's down. Maybe it looks something like this, and it has its 2 hydrogens. And so what's keeping these guys from getting compressed, what's keeping this block of ice from going down further, is the repulsion between the electrons in this molecule and the electrons in that molecule. So on a macro level, we view this as kind of a contact force. But on a microscopic level, on an atomic level, it's really just electromagnetic repulsion at work. What I want to do in this video is think about how the normal force might be different in different scenarios. And since my 2.5-year-old son is obsessed with elevators, I thought I would focus on those. So here I've drawn 4 scenarios, and we can imagine them almost happening in some type of sequence. So in this first picture right over here, I'm going to assume that the velocity is equal to 0, or another way to think about it is this elevator is stationary. And everything we're going to be talking about in this video, I'm talking about in the vertical direction. That's the only dimension we're going to be dealing with. So this is 0 meters per second in the vertical direction. Another way to think about it, this thing is not moving. Now also, it is also, this may be somewhat obvious to you, but its acceleration is also 0 meters per second squared in this picture right over here. Then let's say that I'm sitting in this transparent elevator and I press the button, and so the elevator begins to accelerate upwards. So in this video right over here, or this screen right over here, let's say the acceleration is 2 meters per second times the j unit vector, because that tells us that we are now in the upward direction. And let's say we do that for 1 second, and then we get to this screen right over here. So we had no velocity. We move, we accelerate. Oh, this is 2 meters per square. It's 2 meters per second. This is acceleration here. So we do that for 1 second, and then at 1 second we stop accelerating. So here in this, once we get to this little screen over here, our acceleration goes back to 0 meters per second squared in the j direction. I'll try that. It's really just 0. But now we have some velocity. We did that for just for the sake of simplicity. Let's say this screen lasted for 1 second. So now our velocity is going to be 2 meters per second in the j direction, or in the upwards direction. And then let's say we do that for 10 seconds. So we travel, at least at the constant velocity, we travel for 20 meters. We travel while we're accelerating too. But we're getting close to our floor, and so the elevator needs to decelerate. The elevator needs to decelerate. So it decelerates. So then it decelerates. The acceleration here is negative 2 meters per second squared times in the j direction. So it's actually accelerating downwards now. It has to slow it down to get it back to stationary. So what I want to do is think about what would be the normal force, the force that the floor of the elevator is exerting on me in each of these situations. We're going to assume that we are operating near the surface of the Earth. So in every one of these situations, if we're operating near the surface of the Earth, I have some type of gravitational attraction to the Earth, and the Earth has some type of gravitational attraction to me. And so let's say that let's just make the math simple. Let's say that I'm some type of a toddler, and I'm 10 kilograms. 10 kilograms. Maybe this is my son. He's 12 kilograms, but we'll keep it simple. So it's 10. This person has let me be clear. He doesn't weigh 10 kilograms. That's wrong. He has a mass of 10 kilograms. Weight is the force due to gravity. Mass is the amount of stuff, the amount of matter there is. That's not a rigorous definition. So the mass of the individual, of this toddler sitting in the elevator, is 10 kilograms. So what is the force of gravity? Or another way to think about it, what is this person's weight? Well, in this vignette right over here, in this picture right over here, it's mass times the gravitational field near the surface of the Earth, 9.8 meters per second squared. Let me write that over here. The gravitational field near the surface of the Earth is 9.8 meters per second squared, and the negative tells you it's going downwards. So you multiply this times 10 kilograms. The force, the downward force, the force of gravity is going to be 10 times negative 9.8 meters per second squared. So negative 98 newtons, and I can say that that's going to be in the j direction. Well, what's going to be the downward force of gravity here? It's going to be the same thing. We're still near the surface of the Earth. We're going to assume that the gravitational field is roughly constant, although we know it slightly changes with the distance from the center of the Earth. But when we're dealing on the surface, we assume it's roughly constant. And so we'll assume we have the exact same force of gravity there. And of course, this person's mass, this toddler's mass, does not change depending on going up 2 floors. So it's going to have the same force of gravity downwards in every one of these situations. In this first situation right here, this person has no acceleration. If they have no acceleration in any direction, we're only concerning ourselves with the vertical direction right here. That means that there must be no net force on them. This is from Newton's first law of motion. But if there's no net force on them, there must be some force that's counteracting this force, because if there was nothing else, there would be a net force of gravity, and this poor toddler would be plummeting to the center of the Earth. So that net force in this situation is the force of the floor of the elevator supporting the toddler. So that force would be an equal force, but in the opposite direction. And in this case, that would be the normal force. So in this case, the normal force is 98 newtons in the j direction. So it just completely bounces off. There's no net force on this person. They get to hold their constant velocity of 0. They don't plummet to the center of the Earth. Now, what is the net force on this individual right over here? Well, this individual is accelerating. There is acceleration going on over here. So there must be some type of net force. Well, let's think about what the net force must be on this person, or on this toddler, I should say. The net force is going to be the mass of this toddler. It's going to be 10 kilograms, times the acceleration of this toddler, times 2 meters per second squared, which is equal to 20 kilogram meters per second squared, which is the same thing as 20 newtons. 20 newtons upwards. 20 newtons upwards is the net force. So if we already have the force due to gravity at 98 newtons downwards, that's the same thing here. 98 newtons downwards. We need a force that not only bounces off at 98 newtons downwards to not only keep stationary, but it's also doing another 20 newtons in the upwards direction. So here we need a force in order for this toddler in order for the elevator to accelerate the toddler upwards at 2 meters per second. You have a net force of positive 20 newtons, or 20 newtons in the upward direction. Or another way to think about it, if you have negative 98 newtons here, you're going to need 20 more than that in the positive direction. So you're going to need 118 newtons. You're going to need 118 newtons now in the j direction. So here, where the elevator is accelerating upward, the normal force is now 20 newtons higher than it was there, and that's what's allowing this toddler to accelerate. Now let's think about this situation. No acceleration, but our velocity is, but we do have velocity. So here we were stationary, here we do have velocity. And you might be tempted to think, oh, there must be, maybe I still have some higher force here because I'm moving upwards. I have some upward velocity. But remember Newton's first law of motion. If you're at a constant velocity, including a constant velocity of 0, you have no net force on you. So this toddler right over here, once the toddler gets to the stage, the net forces are going to look identical over here. And actually, if you're sitting in either this elevator or this elevator, assuming it's not being bumped around at all, you would not be able to tell the difference because your body is sensitive to acceleration. Your body cannot sense its velocity if it has no air, if it has no frame of reference, nothing to see passing by. So the toddler there, it doesn't know whether it is stationary or whether it has constant velocity. It would be able to tell this. It would feel that kind of compression on its body. That's what its nerves are sensitive to, or its perception is sensitive to. But here, it's identical to the first situation. Newton's first law tells us there's no net force on this. So it's just like the first situation. The normal force, the force of the elevator on this toddler's shoes, is going to be identical to the downward force due to gravity. So the normal force here is going to be 98 newtons. Completely nets out the negative 98 newtons. So it's in the J direction, the positive J direction. And then when we're about to get our floor, we are about to get to our floor, what is happening? Well, once again, we have a net acceleration. We have a net acceleration of negative 2 meters per second. So if you have a negative acceleration, so once again, what is the net force here? The net force over here is going to be the mass of the toddler, 10 kilograms, times negative 2 meters per second. Negative 2 meters, this is right here, the J direction, that's the vertical direction. Remember, J is just the unit vector in the vertical direction facing upwards. So negative 2 meters per second squared in the J direction, and this is equal to negative 20 kilogram meters per second squared in the J direction, or negative 20 newtons in the J direction. So the net force on this is negative 20 newtons. So we have the force of gravity at negative 98 newtons in the J direction. So we're not fully compensating for that, because we're still going to have a net negative force while this child is decelerating. And that negative net force is a negative force of negative 20. So we're only going to have 78. We're only going to have a 78 newton normal force here that counteracts all but 20 newtons of the force due to gravity. So this right over here is going to be 78 newtons in the J direction. And so I really want you to think about this. And I actually really want you to think about this next time you're sitting in the elevator. The only time that you realize that something is going on is when that elevator is really just accelerating, or when it's just decelerating. When it's just accelerating, you feel a little bit heavier. And when it's just decelerating, you feel a little bit lighter. I want you to think a little bit about why that is. But while it's moving at a constant velocity or stationary, you feel like you're just sitting on the surface of the planet someplace. A little bit heavier, and when it's just This is a picture of the planet Lubricon 6. And Lubricon 6 is a very special planet because it's made up of a yet to be discovered element called Lubrica. And Lubrica is special because it slides across the surface of Lubrica, it will experience absolutely no friction. So if this right over here is a sheet of Lubrica looking at it from the side, and if we have a brick on top of it, maybe gliding on top of it like that, it experiences absolutely no friction. Now, the other things we know about Lubricon 6 is it's drifting into deep space, and it does not have an atmosphere. In fact, it is a complete vacuum outside. It's in such deep space, such a remote part of space, that there aren't even a few hydrogen atoms right over here. It's a complete, absolute vacuum. And it's also an ancient planet. The star that it used to orbit around has long since died away. So it's just this lonely planet drifting in deep space without an atmosphere. The other thing we know about Lubricon 6 is that it is a perfect sphere. It is a perfect sphere. Now, my question to you, for some bizarre reason, there happens to be on the surface of Lubricon 6, so this right over here is the surface of Lubricon 6, there happens to be a sock that is frozen in a block of ice. So this is my sock, and it's frozen. It's frozen in this block of ice. And it happens to be traveling at 1 kilometer per hour. 1 kilometer per hour in that direction. If we look at it from this kind of macro scale, when we're looking at the planet, let's say that that is the frozen sock, and it is traveling along the equator. It is traveling along the equator of Lubricon 6. So my question to you, given all the assumptions we made, that it has absolutely no atmosphere, it's a perfect sphere, and Lubrica has absolutely no friction regardless of what's traveling on top of it, what will happen to this rock, or I should say to this frozen sock, over time? To answer that question, we need to think about all of the forces that are acting on this frozen block of ice and sock. And first of all, let's think about the forces that are acting in the radial direction, inward or outward of the center of the planet. Well, this planet has a mass, and so you have an inward force towards the planet's center of mass. And so you have the force of gravity acting on this block, going radially inward to the center of the planet. So I'll draw it like this. So we have our force of gravity. We have our force of gravity going radially inward, just like that. But then we know that the block is not just spiraling towards the center of the Earth. We have the surface here. It's not going to go through the surface of Lubrica. We can also assume that Lubrica is a very, very, very strong material. And so you also have a normal force. You also have a normal force that is keeping the block from spiraling towards the center of the Earth. So this is a normal force. And one thing we'll think about now, we'll address it directly in another tutorial, is whether this normal force is equal to the force of gravity. We'll think about that in a future video. But these are all the forces that are acting in the radial direction, either inward or towards the center of the planet or outward.
But if we think about it in the tangential direction, along the surface of the planet, there are no net forces. And because there are no net forces in this tangential direction right over here, this block will not either accelerate nor decelerate. There is no air friction. There is no friction, or I should say air resistance, which is really just friction with the particles that you had in the atmosphere. It's a complete vacuum, so there's nothing there. There is no friction with the surface of the planet, so there's no friction there, which could have been a force in the tangential direction. So there's absolutely no forces in the tangential direction. So this block of ice will actually continue to travel at 1 kilometer per hour for all of eternity. So we'll just continue to do it, given the assumptions we just made. Let's continue with our study of the planet Lubricon 6. Now, the one thing I did not tell you in the last video is that Lubricon 6 is not rotating at all. And because it's not rotating, it can really not have an equator. So when we talked about the path of this frozen sock, instead of saying it's traveling across the equator, I should say it's traveling along a great circle. If you assume Earth is a sphere, it's not a perfect sphere, but if you assume it's a sphere, our equator would be a perfect sphere. But in order to have an equator, you need to have some rotation. This right over here, we'll just say it's traveling along the largest possible circle that it can travel along. It's traveling along one of the great circles of this sphere, this block of sock back over there. And now that we know it's not rotating, I want to enter another thought experiment, because this little frozen block of sock is not the only thing that's on the surface of Lubricon 6. Over here, we're reviewing it at a distance. Right over there, if we were to zoom in, you would see sitting on the surface of Lubricon 6. Sitting on the surface of Lubricon 6, so once again, that's the surface, is a frozen banana. So this right over here is a block of ice, and in that block of ice, we have a banana. It's a frozen banana. So that's my best attempt at drawing our banana. And this, relative to the surface of Lubricon 6, is absolutely stationary. It has absolutely no tangential velocity, like this block had and will continue to have for all eternity. This has absolutely no tangential velocity. And so my question for you, if we think about what are the forces acting on this? Well, we have the force of gravity towards the center of Lubricon 6. So we have the force of gravity, and I'm drawing all the forces from the center of mass of this block of banana. So once again, we draw the same part. We have the force of gravity acting radially inward. The force of gravity acting radially inward. And then we know that this banana is not plummeting straight into the center of the Earth. There must be some other net force or some other force that is keeping it stationary. And that force is the force of the surface of Lubricon 6 on the banana or on this block that's keeping it from plunging towards the center of the planet. So that in this case is the normal force. That is the normal force. So that is.
I'll be back.
This is the normal force. And my question to you is, are these two things equal in the case of the banana? Well, as far as we can tell, this banana is completely at rest. This plant right over here, at least relative to the planet, this plant right here has absolutely...
It's like a shake.
It's good.
You want it? You'll probably like it.
One sip, please.
You want it?
One sip, please. Bleh.
You didn't even try it. Like, actually try it. You gotta try it.
I did.
You didn't. No, you tried the powder. You have to try it. Try it.
I did.
No, try it. You still didn't try it. Oh my god.
Take it.
Sure. Well, it's a weight gainer.
You said you're gonna lose it. You're gonna lose it or gain it. Pick one.
Always flipping. Flip face, flop face. Flip face, flop face.
I know.
Flip face, flop face. Remember, we're going to do some running today, right?
Yeah. So if you eat, drink that, and run, you're gonna have some pain in your stomach.
Oh yeah.
Yeah. It's in your stomach, so it's like, oh, it hurts, my rib, my rib.
Maybe I'll just do some jogging or something.
no rotation, and this banana has no relative motion towards the planet. It is not accelerating in absolutely any direction. And if it's not accelerating in any direction, the net forces on it in any dimension must be zero, or all of... the forces must cancel out with each other. So in the case of this banana, the normal force exactly cancels out the force of gravity. These two things, the normal force is exactly equal to the inward force of gravity. Or I guess we should say that they add to zero. They're going in opposite directions. So I should say the normal force plus the force of gravity plus the force of gravity, they're going to be equal zero. They have the same exact magnitude. They're going in opposite directions. So when you add them together, they are going to cancel out. Now, with that little thought experiment out of the way, let's return to the frozen sock. The frozen sock, as we already learned, is orbiting around this planet at an altitude of zero for all eternity at 1 kilometer per hour. And we know that it has the force of gravity is acting on it towards the center of the planet. And there is a normal force that's keeping it from plummeting, from spiraling towards the center of the planet. But my question to you is, in the case of the frozen sock right over here, are these two forces equal like they are for the banana? So in the case of the frozen sock, the traveling orbiting sock, if these two forces had the same magnitude, or essentially they had the same magnitude but just going in opposite directions, the way we draw it down here, they would completely cancel out, and then we would have no net force. So let me make it clear. If the normal force plus the force of gravity cancel out with each other, if this equals zero, then we would have absolutely no net force. No net force. And the object would not accelerate in any direction. An object in motion will stay in motion. So this one right over here, if it had no net force acting on it, it would not stay on the surface of the planet. It would just travel in a straight line, in a tangential line, from where it happens to be this moment forever. If it was right over here, I know this is the path, it would just keep traveling forever off the surface of the planet. We know that clearly is not what's happening. It is orbiting around the planet. It has a circular path. And since it has a circular path, so if I were to draw a cross-section of its, or look at its path from the side, it has a circular path like that. It is going like that. It is constantly being accelerated. It is constantly being accelerated inward. There is some centripetal acceleration going on, inward acceleration. So in order for that inward acceleration to be going on, there must be some net inward force. So in this situation, for the stationary banana, these two guys cancel each other out. But for the case of the moving frozen sock, the sock that is orbiting for all of eternity, it is in orbit. It has a circular path. So there are centripetal motion. There is some net inward force going on here. So in this situation, the magnitude of the force of gravity, is going to be greater than the magnitude of the normal force. So we don't have this situation. That situation we would orbit. So we have a situation where you do have some net centripetal force. The force of gravity, the magnitude of it, is slightly larger than the magnitude of the normal force. An interesting thing to think about if you might invest in the future.
And so it's dying. Like I've been charging it for like 3 hours and it's dying.
Okay.
Yeah,
Let
but
me just use a charger. Charge it up quick with the actual charger.
honey, you know what? Oh my God, this is Calhoun Community College in Alabama. Was it? Thank you.
Yeah.
Named after
who?
John C. Calhoun. And he appears here. Seven defenders of slavery. Defenders.
What?
He's a strong defender of
Oh my
slavery.
goodness! Wow, are you sure it's the same person?
Yes, he's the 7th Vice President of the United States. He's a strong supporter of states' rights and of the use of slavery. Oh my freaking god.
Wow. Okay. Well, there you go. Strong kind of slavery.
Tutorial.
I don't know what to tell you.
Is what would happen if this started going faster and faster and faster? If the frozen sock were to accelerate, what then? How would the relationship between these two things potentially change, if they change at all?
Let's say I have some type of a block here, and let's say this block has a mass of m. So the mass of this block is equal to m, and it's sitting on this. You can do this as an inclined plane or a ramp or some type of wedge. And we want to think about what might happen to this block, and we'll start thinking about the different forces that might keep it in place or not keep it in place, and all of the rest. So the one thing we do know is if this whole setup is near the surface of the Earth, and we'll assume that it is for the sake of this video, that there will be the force of gravity trying to bring or attract this mass towards the center of the Earth, and vice versa, the center of the Earth towards this mass. So we're going to have some force of gravity right at the center of this mass right over here, and so you're going to have the force of gravity. The force due to gravity is going to be equal to the gravitational field near the surface of the Earth. And so we'll call that G. We'll call that G times the mass. That's right, the mass times the gravitational field near the surface of the Earth. And it's going to be downwards, we know that, or at least towards the surface of the Earth. Now, what else is going to be happening here? Well, it gets a little bit confusing because you can't really say that you can't say the normal force is acting directly against this force right over here. Because remember, the normal force acts perpendicular to a surface. So over here, the surface is not perpendicular to the force of gravity. So we have to think about it a little bit differently than we do if this was sitting on level ground. Well, the one thing that we can do, and frankly that we should do, is maybe we can break up this force, the force due to gravity. We can break it up into components that are either perpendicular to the surface or that are parallel to the surface. And then we can use those to figure out what's likely to happen, what are the potentially netting forces or balancing forces over here. So let's see if we can do that. Let's see if we can break this force vector, the force due to gravity, into a component that is perpendicular to the surface of this ramp, and also another component that is parallel to the surface of this ramp. We'll do that in a different color. That is parallel to the surface of this ramp. And I'll use this is a little bit unconventional notation, but I'll call this one over here, I'll call this the force due to gravity that is perpendicular to the ramp. A little upside down T, I'm saying it's perpendicular because it shows the line perpendicular to, I guess, this bottom line, this horizontal line over there. And this blue thing over here, I'm going to call this the force, or the part of force due to gravity that is parallel. That is parallel. I'm just doing two upward vertical bars to show something that is parallel. It's parallel to the surface. So there's a component of force due to gravity, this perpendicular component of force that is parallel. So let's see if we can use a little bit of geometry and trigonometry, given that this wedge is at a theta degree incline relative to the horizontal. If you were to measure this angle right over here, you would get theta. So in future videos, we'll make it more concrete, like 30 degrees or 45 degrees, whatever. Let's just keep it general. If this is theta, let's figure out what these components of the gravitational force are going to be. Well, we can break out our geometry over here. This, I'm assuming, is a right angle. And so if this is a right angle, we know that the sum of the angles in a triangle add up to 180. So this angle, if this angle, and this 90 degrees, right angle says 90 degrees, add up to 180, and that means that this one and this one need to add up to 90 degrees. Or if this is theta, this angle right over here is going to be 90 minus theta. Now, the other thing that you may or may not remember from geometry class is if I have two parallel lines, here, then I have a transversal. So I'm going to assume this line is parallel to this line, and then I have a transversal. So let's say I have a line that goes like this. We know from basic geometry that this angle is going to be equal to this angle, which are alternate interior angles. We prove it in the geometry module or the geometry videos, but hopefully this makes a little bit of intuitive sense. You can even think about how these angles would change as the transversal changes and all the rest. But the parallel line makes this angle similar to that angle, or actually makes it identically congruent. This angle is going to be the same measure as that angle. So can we apply that anywhere over here? Well, we have, no, it's not obvious. This line is perpendicular to the surface of the Earth, right over here that I'm kind of shading in blue. And so is this force vector. It is also perpendicular to the surface of the Earth. So this line over here and this line over here in magenta are going to be parallel. I can even draw that. That line and that line are both parallel. When you look at it that way, you'll see that this big line over here can be viewed as a transversal. Or you could have this angle and this angle are going to be congruent. They're going to be alternate interior angles. So this angle and this angle, by the exact same idea here, it just looks a little bit more confusing here because I have all sorts of things. But this line and this line are parallel. You can view this right over here as a transversal. So this and this are congruent angles. So this is 90 minus theta degrees. This too will be 90 minus theta degrees. 90 minus theta degrees. Now, given that, can we figure out this angle? Well, one thing, we're assuming that this yellow force vector right here, we're assuming that it's perpendicular to the surface of this plane, or perpendicular to the surface of this ramp. So that's perpendicular. This right here is 90 minus theta. So what is this angle up here going to be equal to? This angle will be in green. What is this angle up here going to be equal to? So this angle plus 90 minus theta plus 90 must be equal to 180. Or this angle plus 90 minus theta must be equal to, let me write this down. I don't want to do too much here. So let's call it x. So x plus 90 minus theta plus this 90 degrees right over here, plus this 90 degrees needs to be equal to 180 degrees. We can subtract 180 degrees from both sides. So you subtract 90 twice, you subtract 180 degrees. You get x minus theta is equal to 0, or x is equal to theta. So whatever the inclination of the plane is, or of this ramp, that is also going to be this angle right over here. And the value to that is that now we can use our basic trigonometry to figure out this component and this component of the force of gravity. And to see that a little bit clearer, let me shift this force vector down over here, the parallel component. Let me shift it over here. And you can see the perpendicular component plus the parallel component is equal to the total force due to gravity. And you should also see that this is a right triangle that I've set up over here. This is parallel to the plane. This is perpendicular to the plane. And so we can use basic trigonometry to figure out the magnitudes of the perpendicular force due to gravity and the parallel force due to gravity. So the magnitude, let's think about it a little bit. The magnitude of the, I'll do it over here, the magnitude of the perpendicular force due to gravity, or I should say the component of gravity that's perpendicular to the ramp. The magnitude of that vector, a lot of fancy notation, it's really just the length of this vector right over here. So the magnitude of this over the hypotenuse of this right triangle. What is the hypotenuse of this right triangle? Well, it's going to be the magnitude of the total gravitational force. I guess you could say that. And so you could say that is mg. We could write it like this, but that's really well, I could write it like that. And so this is going to be equal to what? We have so looking at this angle right here, we have the adjacent over the hypotenuse. Remember, so this is a new color. This is a new color. So TOA. Cosine is adjacent over hypotenuse. So this is equal to cosine of the angle. So cosine of theta is equal to the adjacent over the hypotenuse. If you multiply both sides by the magnitude of the hypotenuse, you get the component of our vector that is perpendicular to the surface of the plane is equal to the magnitude of our gravity, or the force due to gravity. The magnitude of the force due to gravity times the cosine of theta. Times the cosine of theta. We'll apply this in the next video just so you can make the numbers a little more concrete. Sometimes just the notation makes things. You'll see it's really pretty straightforward. And then the second thing, we use the same logic. We have the parallel vector right over here. The magnitude of the force, of the component of the force due to gravity that is parallel to the plane, over the magnitude of the force due to gravity, which is the magnitude of mg, that is going to be equal to what? Well, we have, this is the opposite side to the angle, and then, so the blue stuff is the opposite side, or at least its length is the opposite side of the angle, and then right over here, this is magnitude of mg, that is the hypotenuse, so you have the opposite over the hypotenuse, opposite over hypotenuse. Sine of an angle is opposite over hypotenuse, so this is going to be equal to the sine of theta. This is equal to the sine of theta. Or you multiply both sides times the magnitude of the force due to gravity, and you get the component of the force due to gravity that is parallel to the ramp is going to be the force due to gravity total times times sine of theta. So if you have these, then hopefully you should see where this came from, because you could all, if you ever have to derive this again when you're 30 years after you took calculus or physics class, you should be able to do it. But if you know this right here, if you know this right here and this right here, we can all of a sudden start breaking down the forces into things that are useful to us. Because we can say, hey, look, this isn't moving down into this plane, so maybe there's some normal force that's completely netting it out in this example. And maybe if there's nothing to keep it up, if there's no friction, maybe this thing will start accelerating due to the parallel force. And we'll think a lot more about that. And if you ever forget these, think about them intuitively. You don't have to go through this whole parallel line and transversal and all that. If this angle went down to zero, then we'll be talking about essentially a flat surface. There is no inclination there. And if this angle goes down to zero, then all of the force should be acting perpendicular to the surface of the plane. So if this went to zero, if the perpendicular force should be the same thing as the total gravitational force, and that's why it's cosine of theta. Because cosine of zero right now is 1, and so these would equal each other. And if this equals 0, then the parallel component of gravity should go to 0, because gravity will only be acting downwards. And once again, if sine of theta is 0, so the force of gravity parallel will go to 0. So if you ever forget, just do that little intuitive thought process, and you'll remember which one is sine and which one is cosine. Let's say that I have a ramp made of ice, maybe a wedge, just an inclined plane made of ice. We'll make everything of ice in this video, so we have negligible friction. So this right here is my ramp made of ice, and this angle right over here, let's just go with 30 degrees. Let's say on this ramp made of ice, I have another block of ice. This is a block of ice. It is a block of ice, shiny like ice is shiny, and it has a mass. It has a mass of 10 kilograms. And what I'm going to do is think about what's going to happen to this block of ice. So first of all, what are the forces that we know are acting? Well, we're assuming we're on Earth and we build, and we're near the surface. Then there is the force of gravity. There's the force of gravity acting on this block of ice, and the force of gravity is going to be equal to, or at least its magnitude, it's going to be the downward direction, and its magnitude is going to be the mass of the block of ice times the gravitational field times 9.8 meters per second squared. So it's going to be 98 newtons downward. So this is 98 newtons downward. Actually, 10 kilograms to write it out. So the force due to gravity is going to be equal to 10 kilograms times 9.8 meters per second squared downward. It's 9.8 meters per second squared downward. That is the field vector for the gravitational field near the surface of the Earth. Sometimes you'll see the negative 9.8 meters per second squared, and then that negative is giving you the direction implicitly, because the convention is normally that positive is upward, negative is downward. We'll just go with this right here. So the magnitude of this vector is 10 times 9.8, which is 98 kilogram meters per second squared, which is the same thing as newtons. So the magnitude here is 98 newtons, and it is pointing downwards. Now what we want to do is break this vector up into the components that are perpendicular and parallel to the surface of this ramp. So let's do that. So first, let's think about perpendicular to the surface of the ramp. So perpendicular to the surface of the ramp. So this right over here is the right angle. And we saw in the last video that whatever angle this over here is, that is also going to be this angle over here. So this angle over here is also going to be a 30-degree angle. And we can use that information to figure out the magnitude of this orange vector right over here. Remember, this orange vector is the component of the force of gravity that is perpendicular to the plane, and then there's going to be some component that is parallel to the plane. I'll draw that in yellow. Some component of the force of gravity that is parallel to the plane. And thirdly, this is a right angle, because this is perpendicular to the plane, and this is parallel to the plane. So they're going to, it's perpendicular to the plane, it's also perpendicular to this vector right over here. So we can use some basic trigonometry like we did in the last video to figure out the magnitude of this orange and this yellow vector right here. This orange vector's magnitude over the hypotenuse is going to be equal to cosine of 30, or you could say that the magnitude of this is 98 times the cosine of 30 times the cosine of 30 degrees newtons. 98 times the cosine of 30 degrees newtons. And if you want the whole vector, it's in this direction, and the direction going into the surface of the plane. And based on the simple trigonometry, we go to this in more detail in the last video. We know that the component of this vector that is parallel to the surface of this plane is going to be 98 sine of 30 degrees. Sine of 30 degrees. Sine of 30 degrees. And this comes straight out of this magnitude, which is opposite to the angle, over the hypotenuse. Opposite over hypotenuse is the sine of an angle. We did all the work together. But I always want to emphasize that this is coming straight out of basic trigonometry. Straight out of basic trigonometry. So once you do that, we know the different components. We can calculate them. Cosine of 30 degrees is square root of 3 over 2. Sine of 30 degrees is 1/2. That's just the thing that we learned. You can derive it yourself in terms of 69 triangles, right? Lateral triangles, or you can use calculus. It's also one of the things we memorize in trigonometry, so no kind of magical trick I did here. And so if you evaluate this, 98 times square root of 3 over 2 newtons tells us that, right in that same orange color, the force, the component of gravity that is perpendicular to the plane, and this kind of implicitly gives us this direction, is perpendicular to the plane. The force, component of gravity that is perpendicular to the plane is equal to 98 times square root of 3 over 2. 98 divided by 2 is 49. 49 times the square root of 3 newtons. And its direction is into the surface of the plane, or downward, or let's write into surface of the plane. Surface of the plane with the surface of the ramp. It's in this direction over here. And I have to do this because it's a vector. I have to tell you what direction it's going. And the component of the force of gravity that is parallel, I drew it down here, but I can shift it up over here, same exact vector. The component of gravity that is parallel to the surface of the plane is 98 times sine of 30, that's 98 times 1/2, which is 49 newtons, and it's going in that direction, or parallel to the surface of the plane. Parallel to the surface of the plane. So what's going to happen here? Well, if these were the only forces acting on it, so if we had a net force going into the surface of the plane of 49 square roots of 3 newtons, if this was the only force acting in this dimension, or the dimension that is perpendicular to the surface of the plane, what would happen? Well, then the block would just accelerate, at least just with this force, it would accelerate downward. It would accelerate into the surface of the plane. But we know it's not going to accelerate. We know that there's this big wedge of ice here that is keeping it from accelerating in that direction. So that it's, at least in this dimension, there will be no acceleration. When I talk about this dimension, I'm talking about in the direction that is perpendicular to the surface of the plane. There will be no acceleration because this wedge is here. So the wedge is exerting a force that completely counteracts the force, the perpendicular component of gravity. And that force, you might guess what it's called. This wedge is exerting a force just like that. It's going to be 98 newtons upward. So I will call it, the wedge is going to be exerting force that is 49 square roots of 3, because this right here is 49 square roots of 3 newtons into, and so this is 49 square roots of 3 newtons out of the surface. And this is the normal force. It is the force perpendicular to the surface that is essentially, you can kind of view as the contact force that in this case, that the surface is exerting to keep this block of ice from accelerating in that direction. We're not talking about accelerating straight towards the center, we're talking about accelerating in that direction. We broke up the force into kind of the perpendicular direction and the parallel direction. So you have this counteracting normal force, and that's why you don't have the block plummeting or accelerating into the plane. Now, what other forces do we have? Well, we have a force that's parallel to the surface. And if we assume that there's no friction, and I can assume there's no friction in this video because we are assuming that it is ice on ice, what is going to happen? There's no counteracting force to this 49 newtons. 49 newtons parallel downwards to the surface of the plane. So what's going to happen? Well, it's going to accelerate in that direction. You have force is equal to mass times acceleration. Force is equal to mass times acceleration. Or you divide both sides by mass, you get force over mass is equal to acceleration. Over here, our force is 49 newtons in that direction, parallel downwards to the surface of the plane. And so if you divide both by mass, divided by mass, so that's the same thing as dividing it by 10 kilograms. Divided by 10 kilograms, that will give you acceleration. That will give you our acceleration. So acceleration is 49 newtons divided by 10 kilograms in that direction, in this direction right over there. 49 divided by 10 is 4.9, and the newtons divided by kilograms is meters per second squared. So then you get your acceleration. Your acceleration is going to be 4.9 meters per second squared, and maybe I could say parallel. That's 2 bars. There you go, right? Parallel downwards to the surface. Now I'm going to leave you there, and I'll let you think about another thing I'll address in the next video, is what if you had this just standing still? If it wasn't accelerating downwards, if it wasn't accelerating and sliding down, what would be the force that's keeping it in a kind of a static state? Think about that in the next video. In the last video, we had a 10 kilogram mass sitting on top of an inclined plane, a plane of 30-degree angle. In order to figure out what would happen to this block, we broke down the force of gravity on this block into the components that are parallel to the surface of the plane and perpendicular to the surface of the plane. And for the perpendicular component, we got 49 times the square root of 3 newtons downwards. It's 98 times this quantity over here. downwards. And we said, look, we don't see this block of ice. We don't see it accelerating downwards into this wedge because the wedge is supporting it. So there must be a counteracting force that the wedge is exerting on the block, and that counteracting force is the normal force of the wedge on the block of ice, and that is exactly opposite to the force of gravity in this direction. The normal force of gravity, I should say, is the normal force of the wedge, and then these completely balance each other out in that normal direction, in that perpendicular direction. And that's why this block is not accelerating either in that direction or in this direction over here. But the one component of the force of gravity that did not seem to have any offset, at least the way we said in the last video, is the force that is, or the component that is parallel to the surface of the plane. And we figured that out to be 49 newtons. It was essentially the weight of the block times the sine of this angle. So we said, look, if there's no other forces, then it would be accelerated in this direction. And to figure out how the rate of acceleration, you take the force in that direction divided by the mass of the block, and you get 4.9 meters per second squared. Now let's say that wasn't happening. Let's say you were looking at the system right over here, and the block is just stationary. Now, for the sake of argument, let's assume it's not ice on ice. Let's assume that they're both made out of wood. And now all of a sudden we have a situation where the block is stationary. If it's stationary, what is necessarily the case? Well, we already determined that if it's not accelerating in this normal direction, in this perpendicular direction, there must be zero net forces on it. But if it's stationary as a whole, then there must be zero net forces in this parallel component as well. So there must be some force counteracting this 49 newtons that wants to take it down the slope. So there must be some force. There must be some force that is counteracting. That force, the component of gravity that wants to take it down, accelerate it down the slope. And the question is, what is this force? We're dealing with a situation now where we're dealing with a stationary block. A block that is not accelerating. So what is that force? I think you know from experience maybe, what is the difference between a block of wood on top of a block of wood and a block of ice on top of a block of ice? A block of ice on top of a block of ice is much more slippery. There's no friction between ice and ice, but there is friction between wood and wood, making it a little more tangible. Maybe we put some sandpaper. On this surface over here, and then it becomes a little bit clearer. The force that is keeping this block from sliding down in this situation is the force of friction. And the force of friction will always act in a direction opposite to the motion if there was not any friction. So what is the potential, I should say, the potential acceleration, I should say the motion, potential acceleration if there was not any friction. So what is the force of friction in this case? Well, if this block is completely stationary, it's not accelerating down the ramp, the force of friction over here is going to be 49 newtons. It's going to be 49 newtons. It's going to be upwards, kind of up the ramp, 49 newtons up the ramp. Now, when I want to think about it, this is something that can be determined experimentally if you have blocks and ramps. Even if you don't have blocks and ramps, as long as you have some way of measuring force, you can do this experimentally. But an interesting question here is, well, how much do I have to push on this block until it starts to move down the ramp? How much do I have to push on it? And let's say you are able to experimentally determine that if you can apply another 1 Newton, so let's say that if you can apply another 1 Newton on this, so above and beyond the parallel force, if you can apply another, actually it's small, if I can apply another 1 Newton, then all of a sudden I can at least get the box to start accelerating down. Not the rate at which it would do naturally, but I can just start to nudge it down. If I give it another push of 1 Newton in the parallel direction. So what is the total force that it has to exactly 1 Newton? So the total force at this point that's acting on it in order to just start to budge it, the total force, I'll call this the budging force. You'll never hear this in traditional class. F sub B for the budging force. The budging force is in the parallel direction. Let's say that is, if I'm applying 1 Newton in this direction, and it already has 49 newtons due to the component of gravity in this direction, then my budging force is 50 newtons. And so an interesting thing that we can determine based on the materials that are coming in contact with each other is just how much force you need to just start to overcome friction. In this case, it's the budging force. That's a term that I made up. An interesting ratio, which tends to hold for given materials pretty well, is the ratio between the amount of force just to budge and the amount of force between the two objects, between how much force they are exerting on each other. And in this case, the amount of force that is being exerted by the wedge on the block is the normal force. It's 49 square roots of 3. So maybe I should say the magnitude of the budging force over the magnitude of the force that is putting these two things in contact. In this case, it is 49 square roots of 3 newtons. So let me write this. I'll write this over the magnitude of the normal force, and that is 49 square roots of 3. We call this the coefficient of static friction. We're going to use this deeply, or a little bit more deeply in other problems, but it tends to hold true for different materials. So that in the future, if you have a different mass, you have this, or maybe a different incline, you have the same materials, you can, given the normal force, you can figure out the budging force. You can figure out exactly how much force you need to put if you know this, which you usually figure out experimentally. So what would be the value in this case? You have 50 newtons over 49 square roots of 3 newtons. So this is 0.72. And then you could use this information right, so we write this down. This is the coefficient of static friction. We call it the coefficient of static friction because this deals with the ratio of the force of friction relative to the normal force. Or I guess the force necessary to just overcome the force of friction, and just kind of get right over that, the most friction that can be applied by kind of the abrasiveness of the two things when the object is stationary. And I'll do a whole video on the difference with how this is different when an object is stationary to when it's moving. A lot of times they're very, very, very close. For certain materials, you have at least a noticeably different coefficient of friction when the object is stationary as opposed to when it is moving. So I'll leave it there. In the next few videos, we'll use coefficients of friction or calculate coefficients of friction to do some more problems. Just realized that I typed in the wrong numbers at the end of the last video when I was trying to put in the calculator. We were trying to determine the coefficient of static friction at 50 newtons divided by 49 square roots of 3 newtons. In the last video, by accident, in the calculator, I still do 49 square roots of 3, 40 square roots of 3. So let's actually calculate it again. 50 divided by 49 times 49 times the square root of 3 gives us the coefficient of static friction of, if we round it, 0.59. It's equal to 0.59. So That's it. I forgot. I did the calculation wrong on the calculator in the last video. I want to make a quick clarification to the last video, and then think about what's friction up to when the block is actually moving. So the last video, we started off with the block being stationary. We knew that the parallel component of the force of gravity in that block was 49 newtons downward, down the slope. And so the block was stationary, we said there must be an offsetting force. And we said that's the force of friction, and it must be 49 newtons upwards. And so they completely net out in that direction. Now what we said is we're going to keep applying a little bit more force until we can budge this block to start accelerating down. And I said I kept applying a little bit more force until I get to 1 Newton, and then the block started to budge. So at that point when it started to budge, I'm applying this 1 Newton over here, right over here. There's already 49 newtons of force, so the component of gravity in this direction. So combined, we're providing 50 newtons to just start budging it, to just overcome the force of friction. But one thing I want to clarify here is this whole time the force of friction was not constant at 49 newtons. When I wasn't messing with this block and the parallel component of the force was 49 newtons, then the force of friction was 49 newtons. When I started to press on it a little bit, apply a little bit of force, maybe I applied a tenth of a newton on top of that, then the force of friction was 49th and 1/10 newton, because it was still providing enough force so that this block was not moving. Then maybe I applied half a newton. And so the total force in the downward direction would have been 49.5 newtons. But if it still was not moving, then the force of friction was still completely overcoming it. So the force of friction at that point must have been 49.5 newtons. All the way up to the combined force in the downward direction being 49.99999 newtons. And then the force of friction was still 49.99999 newtons. All the way until I hit 50 newtons, and then the block started to budge, which tells us that the force of friction now all of a sudden, or at least the force of static friction, all of a sudden now couldn't keep up and it started to accelerate down. So in that static scenario, the force of friction changed as I applied more or less force in this downward direction. Now with that out of the way, let's take a different scenario. Let me just redraw that same block. All of this is getting messy. So we have the same block. As we said in the last video, we're now assuming this is wood on wood. So this is the wedge. This is the block right over here. We know that the component of gravity that is parallel to the plane right there is 49 newtons. We know that this is 49 newtons. We know the component of gravity that is perpendicular to the plane, we figured out this 2 videos ago, is 49 square roots of 3 newtons. 49 square roots of 3 newtons. We know that this block is not accelerating in this normal direction, so there must be some force counteracting gravity in that direction, and that's the normal force of the wedge on the block. So that is going in that direction at 49 square roots of 3 newtons. And now, instead of assuming that this block is stationary, let's assume that it's moving with a constant velocity. So now we're dealing with a scenario where the block has a constant velocity. And for the sake of this video, we'll assume that constant velocity is downward. So the constant velocity v is equal to, I don't know, let's say it is 5 meters per second down the wedge, or down the ramp, or I guess we can say the direction that is parallel to the surface of the ramp. So it's in this direction right over here. So that's the constant velocity. So what are all the forces at play? And be very careful here. There might be a temptation to, okay, there's a net force here, we're moving, so maybe that's the net force that's causing the movement. Remember, this is super important. This is Newton's first law. If you have a net force, if you have an unbalanced force, it will cause it to accelerate. And we are not accelerating here. We have a constant velocity. We are not accelerating here. So if you're not accelerating in that direction, then that means that the force in that direction must be balanced. So there must be some force acting in the exactly opposite direction. There must be an offsetting force.
Hold on. Yeah. Oh no, it's a sin. Yeah. Okay.
Force. We said that's the force of friction, and it must be 49 newtons upwards. And so they completely net out in that direction. Now what we said is we're going to keep applying a little bit more force until we can budge this block to start accelerating down. And I said I kept applying a little bit more force until I get to 1 Newton, and then the block started to budge. So at that point when it started to budge, I'm applying this 1 Newton over here, right over here. There's already 49 newtons of force, so the component of gravity in this direction. So combined, we're providing 50 newtons to just start budging it, to just overcome the force of friction. But one thing I want to clarify here is this whole time the force of friction was not constant at 49 newtons. When I wasn't messing with this block, and the parallel component of the force was 49 newtons, then the force of friction was 49 newtons. When I started to press on it a little bit, apply a little bit of force, maybe I applied a tenth of a newton on top of that, then the force of friction was 49th and 1/10 newton, because it was still providing enough force so that this block was not moving. Then maybe I applied half a newton. And so the total force in the downward direction would have been 49.5 newtons. But if it still was not moving, then the force of friction was still completely overcoming it. So the force of friction at that point must have been 49.5 newtons. all the way up to the combined force in the downward direction being 49.999999 newtons, and then the force of friction was still 49.9999 newtons, all the way until I hit 50 newtons, and then the block started to budge, which tells us that the force of friction now all of a sudden, or at least the force of static friction, all of a sudden now couldn't keep up and it started to accelerate down. So in that static scenario, the force of friction changed as I applied more or less force in this downward direction. Now with that out of the way, let's take a different scenario. Let me just redraw that same block since all of this is getting messy. So we have the same block. As we said in the last video, we're now assuming this is wood on wood. So this is the wedge. This is the block right over here. We know that the component of gravity that is parallel to the plane right there is 49 newtons. We know that this is 49 newtons. We know the component of gravity that is perpendicular to the plane, we figured out this 2 videos ago, is 49 square root of 3 newtons. 49 square root of 3 newtons. We know that this block is not accelerating in this normal direction, so there must be some force counteracting gravity in that direction, and that's the normal force of the wedge on the block. So that is going in that direction. That's 49 square roots of 3 newtons. And now, instead of assuming that this block is stationary, let's assume that it's moving with a constant velocity. So now we're dealing with a different color. So now we're dealing with a scenario where the block has a constant velocity. And for the sake of this video, we'll assume that constant velocity is downward. So the constant velocity v is equal to, I don't know, say it is 5 meters per second down the wedge or down the ramp, or I guess we can say the direction that is parallel to the surface of the ramp. So it's in this direction, right? So that's the constant velocity. So what are all the forces at play? And be very careful here. There might be a temptation to, okay, there's a net force here, we're moving, so maybe that's the net force causing the movement. Remember, this is super important. If you have, this is Newton's first law. If you have a net force, if you have an unbalanced force, it will cause it to accelerate. And we are not accelerating here. We have a constant velocity. We are not accelerating here. So if you're not accelerating in that direction, that means that the force in that direction must be balanced. So there must be some force acting in the exactly opposite direction that keeps this thing from accelerating downwards. And so it must be exactly 49 newtons in the opposite direction. And as you can imagine, this is the force of friction. This right over here is the force of friction. And the difference between this video and the last video is last time friction was static. Even at 49 newtons, the box was stationary. You had to keep nudging until you get to 50 newtons, then it started moving. Here, we're just jumping into this picture where we just see a box that's moving down the slope at 5 meters per second. So we don't know how much force it took to overcome static friction, but we do know that there is some force of friction that is keeping this box from accelerating. It's keeping it at a constant velocity. That is completely negating the parallel component of the force of gravity, parallel to the surface of this plane. So given this, let's calculate another coefficient of friction. This is going to be the coefficient of kinetic friction, because now we are moving down the block. And I'll do a video on why sometimes the coefficient of static friction can be different than the coefficient of kinetic friction. So the coefficient of kinetic friction, we'll write, so this is the Greek letter mu, okay, Greek letter mu, and it's a little lowercase k here for kinetic, or it's kind of say moving friction, is going to be equal to the force of friction. So it's going to be, or I should say the magnitude of the force of friction, the magnitude of the force of friction over the normal force, or I should say the magnitude of the normal force. And you can derive this experimentally. One, if you just observe this whole thing going on, you do the mass of the block, you do this with the component of gravity that's going in this direction. If you do this angle is 30 degrees from the last situation, you can figure out this coefficient of kinetic friction. And what's cool about this is in general going to be true for any two materials that are like this. So this is a certain type of wood on a certain type of wood, or a certain type of sandpaper on a certain type of sandpaper, whatever you're talking about. And then you can use that to make predictions if the incline was different, or if the mass was different, or even if you were on a different planet, or someone was pressing down on this block, it would change the normal force. So given this right here, let's figure out, let's see, we get the coefficient of kinetic friction here. The force of friction here, completely offsetting the parallel force of gravity, parallel to the surface, is 49 newtons. And the normal force here, the force of contact between these two things, this block and this wedge, is 49 square roots of 3 newtons. 49 square roots of 3 newtons. So we get 1 over the square root of 3 equals 0.58. And there's no units here, because the units can't slide. It's a unitless measurement. Now the interesting thing here is that the coefficient, the way I've set up this problem, the coefficient of kinetic friction is lower, if we assume the same materials, than the coefficient of static friction was. And for some materials, they might not be that different, but for other materials, the kinetic friction can be lower than static friction. You never see a situation where static friction is lower, the coefficient of static friction, that I know of, is lower than kinetic friction. But you do see situations where the coefficient of kinetic friction is lower than the coefficient of static friction. That once something is moving, for some reason, we'll theorize why that might be. For some reason, friction is a little less potent than when something is stationary. So we can say this generally: the coefficient of kinetic friction is less than or equal to the coefficient of static friction. It's a little bit easier, or friction provides a little less, or less than, or equal to the force when something's moving than when something is stationary. So I'll think about that a little bit deeper in the next video. It's a little bit easier. The kinetic friction is less than, or we can say this generally: the coefficient of kinetic friction is less than or equal to the coefficient of static friction. It's a little bit easier, or friction provides a little less, or less than, or equal to the force when something is moving than when something is stationary. So I'll think about that a little bit deeper in the next video. I will now introduce you to the concept of tension. So tension is really just a force that exists within or applied by a stream of fluid. It's usually just something cool. So let's say I have a weight. Let's say it's suspended from this wire, which is right this system, which is attached to this wire. We already know that, of course, along this line, this weight is being pulled down. I will now introduce you to the concept of tension. So
So it's tension is really just a force that exists within or applied by a string of wire. So we should just do something. So let's say it's suspended from this wire, which is attached to this. We already know that, of course, we're on this planet. This weight is being pulled down by gravity, right? We already know that downward force on this weight is gravity. Right? We also know that this weight isn't accelerating, and it's actually stationary. Also, lots of important things, it's not accelerating. So, but given that, we know that the net force of it must be zero by Newton's laws. So, what is the counteracting force? Well, we can attention and say, well, the spring's pulling on it, right? The string is what's keeping the weight from falling. So, the force that the string or this wire applies to this weight is the force of tension. And that is also another thing about it, because that's also the force that's within the wire. And that is going to exactly offset the force of gravity. And that's what keeps this point right here. That's what keeps this point right here stationary, keeps it from accepting. That's pretty straightforward. Tension is just force and strain. And just so you can conceptualize it, on a guitar, the more you pull on some of the higher hinge strings, the more you pull on it, the higher the tension actually gets, the higher the tension. So you've dealt with tension a lot. I think actually when they set up on some strings, you'll probably tell you the tension that wire string supports. So tension is something that should be hopefully a little bit. So let's, with that fairly simple example, let's create a slightly more complicated. So let's take the same, instead of making the same here, let's add two more strings. Let's add this green string. Green string here. It's attached to the same. That's the same. Let's say this is all.
The theory of gases.
My question to you is, what is the tension in these two strings? Well, like the first problem, this point right here is stationary. It's not accelerating in either the left-right directions, and it's not accelerating in the down directions. So we know that the net forces in both the x and y dimensions must be zero. My second question to you is, what is going to be the offset? Because we know already that at this point right here, it's going to be a downward force, right? You can assume that the wires have moving. So we know that there's going to be a downward force here. So there's gravity, right? Full weight of this entire object, weight of this wires pulling down. So what is going to be the upward force here? Well, let's look at each of the wires. This second wire, T2, or yes, the second one.
Okay.
Wire is just pulling left. It has no y coordinate.
All right, guys, I'm gonna go to gym. Start running. Take care, everyone. Peace.